Hello and welcome to Space Historians. I'm truly glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our little blue world. Tonight, we're not racing through the stars, we're gliding gently, letting the silence of space wrap around us like a soft blanket. This is your moment to leave behind the noise of the day and step quietly into the vast, starlit corridors that exist between solar systems, between suns, in the quiet fabric of the Milky Way itself. Before we begin, I'd love to know, where in the world are you listening from, and what time is it where you are? It always amazes me how, while the night sky may look different across the globe, the stars above have watched over every civilization in history. And between those stars, in the darkness we rarely think about, lies a story older than any kingdom, any language, any life. If you enjoy these quiet journeys through time and space, a like and a subscribe help keep this channel orbiting steadily. And for those who've already joined this growing constellation of listeners, thank you. You are part of this voyage, part of this shared wonder. Each episode here isn't just about stars, planets, or galaxies. It's about the stories they hold, the myths whispered by ancient astronomers, the discoveries that changed how we see the universe, and the quiet mysteries still waiting to be revealed. So tonight, as your eyes grow heavy and your breathing slows, imagine yourself floating slowly past the edge of Earth's atmosphere. The air grows thin, the blue fades to black, and there a vast canvas of history and starlight stretches out before you. Every shimmering star is a chapter, every faint glow is a story. But tonight we'll linger not on the stars themselves, but on what exists in the spaces between them. If you gently press the notification bell, you'll always know when the next journey begins. But for now, you don't need to do anything but listen, breathe, and drift. Let's travel together, back through the ages of space exploration, ancient stargazers, and the endless unknown. Welcome to the quiet side of the cosmos. When you look up at the night sky, what do you see? You see stars, pinpricks of light scattered across the dark. You see planets, if you know where to look. Maybe the soft glow of the Milky Way itself, that hazy band of brightness stretching overhead. But here's something most people never consider, something that changes everything once you know it. Most of the galaxy isn't made of stars at all. In fact, most of the Milky Way, the vast spiral we call home, is composed of the space between those stars. The emptiness, the silence, the dark stretches that seem to hold nothing but shadow. And yet, those spaces are not empty, not even close. They are filled with something ancient, something invisible, something that connects every solar system in the galaxy into a single, breathing whole. Scientists call it the Interstellar Medium, but you can think of it as the ocean between islands of light, a sea so thin, so faint, that you could travel billions of kilometers through it and never collide with a single grain of matter. Yet without it, there would be no stars, no planets, no life. This is the paradox at the heart of our galaxy. What looks like nothing is actually everything. Imagine spreading a single grain of sand across a space the size of a football field. That's roughly how sparse the matter is in interstellar space. 1 atom per cubic centimetre. In comparison, the air you're breathing right now contains about 10 billion trillion molecules in that same space. The difference is so extreme it defies human intuition. And yet, even in that vast thinness, entire systems are born. The interstellar medium is not uniform. It's a patchwork of regions, some cold and dark, others hot and glowing. There are clouds of hydrogen gas drifting between stars, dense enough to block light. There are wisps of ionized plasma heated by the radiation of nearby suns. There are filaments of cosmic dust, tiny grains of carbon and silicon, left behind by dying stars and scattered across light years. And there are magnetic fields threading through it all, invisible highways along which charged particles flow. When a massive star dies, it doesn't simply vanish. It explodes in a supernova, one of the most violent events in the universe. The outer layers of the star are flung into space at thousands of kilometers per second, carrying with them all the heavy elements forged in the star's core. Carbon, oxygen, nitrogen, iron, gold. These elements mix with the interstellar gas, enriching it, changing its chemistry. Over millions of years, that enriched gas drifts through space, carried by galactic winds and the slow rotation of the Milky Way itself. Eventually, gravity begins to pull some of that gas together. It collects in vast clouds, hundreds of light years across, cold and dark. Within those clouds, denser pockets form. The gas collapses under its own weight. Temperatures rise, pressure builds. And finally, at the heart of the cloud, nuclear fusion ignites. A new star is born. Around it, leftover gas and dust clump together, forming planets, moons, asteroids. A new solar system emerges from the remnants of old ones. This is the cycle that has shaped the Milky Way for billions of years. Stars are born from the interstellar medium. They live, they shine, they die, and they return their matter to the medium. The spaces between solar systems are not voids, they are nurseries, graveyards, libraries of cosmic history. Every breath you take contains atoms that once floated in that ancient sea. The carbon in your cells was forged inside a star that died long before the sun existed. That star exploded, scattering its contents across the galaxy. Those atoms drifted through interstellar space for hundreds of millions of years, carried by invisible currents, until they eventually settled into the gas cloud that gave birth to our solar system. Over billions of years, they found their way into Earth, into the atmosphere, into living things, into you. You are made of the space between stars, literally. This isn't poetry, it's physics, it's chemistry, it's the documented history of matter in the universe. Every element heavier than hydrogen and helium was created inside a star and released into interstellar space when that star died. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was once part of that invisible ocean. So when we talk about what lies between solar systems, we're not talking about emptiness. We're talking about the connective tissue of the galaxy, the medium through which light travels, through which energy flows, through which matter cycles endlessly between life and death and life again. The distances involved are almost impossible to grasp. Our nearest stellar neighbour, the Alpha Centauri system, lies more than 4 light-years away. That's roughly 40 trillion kilometres. If you could travel at the speed of a commercial jet, it would take you over 5 million years to get there. And in all that distance, you would pass through a region where the density of matter is so low that it makes the best vacuum chambers on Earth look crowded by comparison. Yet even in that vast emptiness, things are happening. Atoms are moving. Photons are streaming past. Magnetic fields are shifting. Cosmic rays are zipping through at nearly the speed of light. The interstellar medium is not static. It's dynamic, humming quietly with the echoes of creation and destruction. From our small planet orbiting one star among hundreds of billions, it's easy to forget that this quiet reaches everywhere. The peace we associate with the night sky, that deep contemplative stillness, is the echo of what fills most of the galaxy. The spaces between suns are not far away. They begin just beyond the reach of our own solar system. We are surrounded by them, sustained by them, part of them. And tonight, as you lie there listening, your body carries the memory of what lies between solar systems. You are in the most literal sense made of the space between the stars. Every atom in you has travelled farther and longer than any spacecraft humanity has ever built. You are stardust, yes, but you are also interstellar dust. You are the product of billions of years of galactic drift, of cosmic recycling, of the slow, patient work of gravity and time. The invisible ocean is real. It surrounds every sun. It connects every world. And understanding it changes everything we thought we knew about the universe, about our place in it, and about the nature of emptiness itself. This is where our journey begins. To understand what lies between solar systems, we first need to understand where one solar system ends and interstellar space begins. The boundary is not as clear as you might think. It's not a line drawn in the dark. It's a gradual transition, a shifting frontier shaped by the invisible wind that flows from our sun. Our sun is not a quiet, static object. It's an active, roiling ball of plasma, constantly releasing energy in all directions. Some of that energy comes in the form of light, the familiar warmth we feel on our skin. But the sun also releases something else, something invisible and relentless. A stream of charged particles, electrons and protons, flowing outward at speeds of hundreds of kilometers per second. This is the solar wind. The solar wind doesn't stop at the edge of the planets. It keeps going, pushing outward into space, creating a vast bubble around the sun. This bubble is called the heliosphere. It's a protective shell, a region where the sun's magnetic field and its wind dominate the environment. Inside the heliosphere, we are still part of the solar system. Outside it, we enter the domain of the galaxy itself. The heliosphere extends far beyond the orbits of the planets, beyond Neptune, beyond the scattered disk of icy objects, beyond even the distant Oort cloud where comets sleep in their long, slow orbits. For decades, scientists could only estimate where the heliosphere ended. They knew it was out there somewhere, but they had no direct measurements. No spacecraft had ever travelled that far. Until Voyager. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2. Their primary mission was to explore the outer planets, Jupiter, Saturn, Uranus, Neptune. They succeeded brilliantly, sending back images and data that transformed our understanding of the solar system. But their mission didn't end there. After visiting the planets, both spacecraft continued onward, moving faster than any human-made object before them, heading toward the edge of the heliosphere. For more than 30 years, the Voyagers travelled through the outer solar system. Engineers on Earth monitored their signals, watching for signs that they were approaching the boundary. They looked for changes in the solar wind, shifts in the magnetic field, increases in cosmic rays from beyond. And slowly, the data began to change. In August of 2012, something extraordinary happened. Voyager 1 crossed the heliopause, the outer edge of the heliosphere. For the first time in history, a human-made object entered interstellar space. The solar wind dropped to nearly zero. The density of plasma increased. Cosmic rays, particles from distant supernovae and other galactic sources flooded the spacecraft's detectors. Voyager 1 had left the Sun's protective bubble and entered the ocean between stars. Voyager 2 followed in November of 2018. Its crossing confirmed what Voyager 1 had found. The heliopause was not a smooth, symmetrical boundary. It was jagged, shaped by the pressure of the interstellar medium pushing back against the solar wind. The Sun's bubble was not a perfect sphere. It was more like a teardrop, stretched in the direction the solar system was moving through the galaxy. This was the setting. This was the edge. Beyond the heliopause, the rules changed. The Sun's influence faded. The magnetic field weakened. The particles that filled the space were no longer products of our star, but remnants of stars that died millions or billions of years ago. The Voyagers had entered a region that had existed long before the Sun was born, and would continue long after it died. But even here, at the edge of interstellar space, the environment was not uniform. The Voyagers detected layers, zones where the density and temperature of the plasma varied. They found unexpected structures, magnetic bubbles and shock waves, evidence of interactions between the solar wind and the galactic medium. The boundary between solar and interstellar space was not a simple line. It was a frontier, a dynamic region where two environments collided and mixed. The heliosphere itself is constantly changing. It expands and contracts as the solar wind fluctuates. During periods of high solar activity, when the Sun releases more energy, the heliosphere swells. During quiet periods, it shrinks. The heliopause moves in and out like a slow tide, shifting by billions of kilometers over the course of the solar cycle. And beyond the heliopause, the interstellar medium presses inward. It's not passive. It has its own currents, its own magnetic fields, its own pressure. The Sun moves through this medium at about 20 kilometers per second, creating a bow shock, a region where the interstellar gas piles up in front of the heliosphere like water in front of a moving ship. This bow shock extends light years ahead of us, marking our passage through the galaxy. From Earth, we cannot see any of this. The heliosphere is invisible. The heliopause is invisible. The interstellar medium itself is invisible. But spacecraft have measured it. Instruments have mapped it. And now we know. Our solar system is not isolated. It's embedded in a larger environment, surrounded by a sea that connects us to every other star in the Milky Way. The transition from solar to interstellar space is not abrupt. It's gradual. As you move outward from the Sun, the density of solar wind particles decreases. The intensity of cosmic rays increases. The magnetic field shifts from solar to galactic. You pass through layers, each with its own characteristics, until finally you reach a point where the Sun's influence is negligible. That's the true beginning of interstellar space. And what do you find there? Silence. Not the absence of activity, but the absence of a single dominant source. Inside the heliosphere, everything is shaped by the Sun. Outside it, you are in the collective environment of the galaxy. The particles around you come from countless stars. The magnetic fields are woven by forces operating on scales of hundreds or thousands of light years. The light comes from every direction, faint and diffuse. The accumulated glow of billions of distant suns. The temperature in interstellar space varies depending on where you are. In some regions, the gas is cold, just a few degrees above absolute zero. In others, it's heated to millions of degrees by shock waves from supernovae or stellar winds from massive stars. But on average, the interstellar medium is cold and dark, a place where matter drifts slowly, where change happens over timescales measured in millions of years. This is the setting. This is where one solar system ends and the space between begins. It's not a wall. It's not a door. It's a gradient, a transition from the local to the galactic, from the influence of one star to the collective environment of many. And it's through this environment that every star in the galaxy moves, each trailing its own heliosphere, each carving its own path through the interstellar sea. The Voyagers are still out there, still sending signals back to Earth. They're more than 20 billion kilometers away now, far beyond the reach of the sun's warmth, drifting through a region that no human has ever directly observed. Their power is fading, their instruments are shutting down one by one, but they're still there, silent witnesses to the space between solar systems. And someday, millions of years from now, they will drift past other stars. They will carry with them a golden record, a message from humanity, a snapshot of life on Earth. But by then, the sun will have moved on, the heliosphere will have swept past their position, and the Voyagers will be adrift in the true interstellar medium, alone in the ocean between stars. This is the setting. This is the frontier. And now that we've crossed it, we can begin to explore what lies beyond. For most of human history, the space between stars was thought to be empty. Perfectly, absolutely empty. A void. The ancient Greeks called it the ether, an invisible substance that filled the heavens, but even that was more philosophy than observation. By the time of the scientific revolution, most astronomers believed that space beyond Earth's atmosphere was a perfect vacuum, a place where nothing existed except the occasional comet or meteor. But in the early 20th century, that assumption began to crack. It started with starlight. Astronomers had been studying the spectra of stars for decades, splitting their light into rainbows and analysing the dark lines that appeared within them. Each line corresponded to a specific element absorbing light at a specific wavelength. By studying these absorption lines, scientists could determine what a star was made of, how hot it was, how fast it was moving. It was one of the most powerful tools in astronomy. But then they noticed something strange. Some of the absorption lines didn't match the stars themselves. They were too narrow, too sharp, too cold. It was as if something between us and the stars was absorbing light, something that wasn't part of the stars at all. In 1904, a German astronomer named Johannes Hartmann was studying a binary star system called Delta Orionis. He noticed absorption lines from calcium that didn't move with the stars. As the stars orbited each other, their spectral lines shifted due to the Doppler effect, but the calcium lines stayed fixed. Hartmann realized that the calcium wasn't in the stars. It was in the space between the stars and Earth. There was gas out there, cold and thin, but real. This was the first direct evidence of the interstellar medium. It wasn't a void. It was filled with matter. Over the following decades, astronomers found more evidence. They detected hydrogen, the most common element in the universe, in the space between stars. They found molecules, carbon monoxide, ammonia, water vapor, floating in cold clouds. They discovered dust grains, tiny particles of carbon and silicon, blocking and scattering starlight. The interstellar medium was not a uniform sea. It was a complex environment with clouds, filaments and voids, each with different temperatures, densities and compositions. But how much matter was actually out there? How dense was the interstellar medium? The calculations were staggering. On average, there was about 1 atom per cubic centimetre. In some regions, like dense molecular clouds, the density could reach hundreds or thousands of atoms per cubic centimetre. In others, like the hot ionized gas surrounding massive stars, It dropped to a fraction of an atom per cubic centimetre. To put this in perspective, the best vacuum chambers on Earth can achieve densities of about 10 billion atoms per cubic centimetre. The interstellar medium is trillions of times thinner than that. It's the closest thing to a perfect vacuum that exists naturally in the universe. And yet, when you add up all the matter in all the space between stars in the Milky Way, it amounts to about 10 to 15% of the galaxy's total mass. Billions of times the mass of the Sun, spread across hundreds of thousands of light years. The discovery of the interstellar medium changed everything. It meant that stars were not isolated. They were embedded in a shared environment, connected by gas, dust, and magnetic fields. It meant that the life cycle of stars was not a closed loop. When a star died, its matter didn't disappear. It mixed with the interstellar medium, enriching it with heavy elements. When new stars formed, they inherited that enriched material, creating planets with rocky surfaces and atmospheres capable of supporting life. The interstellar medium was not passive. It was active, dynamic, constantly changing. Shock waves from supernovae ploughed through it, compressing gas and triggering new waves of star formation. Stellar winds from massive stars carved bubbles and cavities in it, creating regions of hot, low-density plasma. Gravity pulled gas into clouds, which collapsed into stars, which eventually died and returned their matter to the medium. It was a cycle, a galactic ecosystem, operating on timescales of millions and billions of years, and it was everywhere. Every gap between solar systems, every dark patch in the night sky, every seemingly empty region of the galaxy was filled with this thin, invisible sea. It was the fabric that held the Milky Way together, the medium through which light travelled, the reservoir from which new stars were born. But the interstellar medium wasn't just hydrogen and dust. It also contained something else, something more mysterious. Cosmic rays. These were not rays in the traditional sense, but high-energy particles, mostly protons, travelling at nearly the speed of light. They came from supernovae, from pulsars, from the violent regions around black holes. They streamed through the galaxy, colliding with atoms in the interstellar medium, ionizing them, creating a faint glow that could be detected by radio telescopes. Cosmic rays were one of the ways energy moved through the interstellar medium. They carried momentum and heat, stirring the gas, preventing it from collapsing too quickly. They also affected the chemistry of the medium, breaking apart molecules, creating ions, driving reactions that wouldn't happen otherwise. In some ways, cosmic rays were the spark plugs of the interstellar medium, keeping it alive and active. And then there were magnetic fields. The interstellar medium was threaded with magnetic fields, generated by the motion of charged particles. These fields were weak, about 1,000,000 times weaker than Earth's magnetic field, but they extended over enormous distances. They shaped the flow of gas, channeling it along field lines, preventing it from moving freely. They trapped cosmic rays, forcing them to spiral along the field lines rather than escaping the galaxy. They played a crucial role in star formation, supporting clouds against gravitational collapse until conditions were right. The discovery of the interstellar medium was not a single moment. It was a gradual realization, built up over decades from thousands of observations. Spectroscopy revealed the gas, radio astronomy revealed the hydrogen, infrared telescopes revealed the dust, X-ray telescopes revealed the hot plasma. Each new instrument added another piece to the puzzle, showing that the space between stars was far richer and more complex than anyone had imagined. By the mid-20th century, astronomers had a fairly complete picture of the interstellar medium. They knew it was made mostly of hydrogen, with traces of helium and heavier elements. They knew it was divided into different phases: cold neutral gas, warm ionized gas, hot coronal gas, each with its own properties. They knew it was shaped by the life and death of stars, by supernovae, by stellar winds, by the slow rotation of the galaxy itself. But they also knew there was more to discover. The interstellar medium was not static. It was constantly evolving, responding to the energy and matter injected into it by stars. It was a living system, and understanding it fully would require decades more of observation and theory. The sea of atoms was real. It was vast, and it was the key to understanding how the Milky Way worked, how stars formed, how planets came to be, and ultimately, how life emerged on a small rocky world orbiting an ordinary star in the suburbs of the galaxy. This was the discovery. This was the revelation. The space between solar systems was not empty. It was full of history, full of potential, full of the raw material for everything that had ever existed and everything that ever would. When Johannes Hartmann published his discovery in 1904, the reaction in the astronomical community was muted, not because his findings were wrong, but because they were so unexpected that most scientists didn't know what to make of them. For centuries, the dominant view had been that space beyond the planets was empty. The idea that there was gas floating between the stars seemed almost absurd. How could something so thin even be detected? How could it matter? But Hartmann's observations were solid. The calcium absorption lines he detected didn't move with the stars. They had to come from somewhere else. And the only reasonable explanation was that there was matter, cold and diffuse, in the space between the stars and Earth. Other astronomers began to look for similar evidence. They found it. More absorption lines from sodium, from potassium, from ionized calcium. All of them pointed to the same conclusion. Interstellar space was not empty. It contained gas, incredibly thin, but real and detectable. The question was, how much? And what did it mean for our understanding of the galaxy? At first, the discovery didn't seem to change much. The interstellar medium was so thin that it had no obvious effect on the orbits of stars or the structure of the galaxy. It was a curiosity, a footnote in the grand scheme of cosmic mechanics. But as more data came in, the picture began to shift. In the 1920s, astronomers began to notice another phenomenon. Some stars appeared dimmer and redder than they should be. The effect was subtle, but it was there. At first, they thought it might be an error in the measurements, or some property of the stars themselves. But eventually, they realized the cause: dust. Tiny particles, smaller than a grain of sand, floating in the space between stars, absorbing and scattering light. Blue light was scattered more than red, making distant stars appear redder than they actually were. This was the same effect that makes Earth's sky blue and sunsets red, but on a cosmic scale. The discovery of interstellar dust was even more surprising than the discovery of gas. Dust meant that the interstellar medium wasn't just atoms floating in the void. It contained solid particles, complex grains made of carbon, silicon, and other elements. These grains were created in the atmospheres of dying stars and released into space when the stars shed their outer layers. Over time, they accumulated in the interstellar medium, forming a thin but pervasive haze that affected how we saw the galaxy. The implications were profound. If interstellar dust could dim starlight, then our measurements of stellar distances and luminosities were wrong. We had been underestimating how far away some stars were, and how bright they truly were. The structure of the Milky Way itself had to be reconsidered. What looked like voids in the galaxy might just be regions where dust blocked the light. What looked like clusters of stars might be scattered populations appearing close together due to the distortion caused by dust. Astronomers had to go back and recalibrate everything. They developed new techniques to account for interstellar extinction, the dimming and reddening of starlight by dust. They measured the dust's distribution, finding that it was concentrated in the plane of the galaxy, forming a thin disk that traced the spiral arms. Found that it was small compared to the gas, maybe 1% of the interstellar medium's total mass, but its effect on observations was enormous. The scientific community's response to these discoveries was a mix of excitement and frustration. Excitement because they had uncovered a new component of the galaxy, something that had been invisible until now. Frustration because it complicated everything. Suddenly, every observation had to be corrected for interstellar effects. Every theory about stellar evolution and galactic structure had to be revised. The universe was messier than they'd thought. But there was also a deeper shift in perspective. The discovery of the interstellar medium forced astronomers to redefine what they meant by emptiness. In physics, a vacuum is defined as a space with no matter. But that definition had always been idealized. In reality, there's no such thing as a perfect vacuum. Even the best laboratory vacuums contain stray atoms. Even the space between galaxies contains faint traces of gas. The universe, it turned out, was never truly empty. This realization had philosophical implications too. For centuries, humans had imagined space as a void, a blank canvas on which the stars were painted. But now it was clear that space itself was a medium, a substance with properties and structure. It wasn't nothing. It was something, just very, very thin. And that something connected everything. Every star, every planet, every galaxy was embedded in this cosmic ocean, influenced by it, shaped by it. The interstellar medium also changed how scientists thought about the origins of stars and planets. Before its discovery, stars were thought to form from collapsing clouds of their own material, isolated from their surroundings. But now it was clear that stars formed from the interstellar medium itself. They were not separate from it, they were products of it. And when they died, they returned their matter to it, enriching it with new elements that would be incorporated into the next generation of stars. This cyclical view of stellar evolution was revolutionary. It meant that the history of the galaxy was not a series of isolated events, but a continuous process. Stars, planets, and even life were all part of the same cycle, connected by the interstellar medium, by the slow mixing of matter across space and time. Some scientists resisted these ideas at first. The notion that space was filled with matter, however thin, seemed to violate the principle of cosmic simplicity. Wouldn't a universe with an interstellar medium be more complicated than one without? Didn't Occam's razor favour the simpler explanation? But the evidence was undeniable. Spectroscopy showed the gas. Photometry showed the dust. Radio astronomy, which emerged in the 1930s, revealed hydrogen emissions from the interstellar medium, confirming its presence beyond any doubt. By the mid-20th century, the debate was over. The interstellar medium was real, and it was fundamental to understanding how the galaxy worked. The first response to the discovery of the interstellar medium was disbelief, then curiosity, then acceptance. But along the way, it transformed astronomy. It forced scientists to rethink their assumptions about space, about stars, about the structure of the Milky Way itself. It showed that the universe was not a collection of isolated objects floating in a void, but an interconnected system where everything was linked by the thin, invisible sea that filled the gaps between stars. and it raised new questions. If the interstellar medium existed, what else was out there that we hadn't detected yet? What other components of the galaxy were we missing? The discovery of the interstellar medium didn't close the book on cosmic emptiness. It opened a new chapter, one that would lead to even stranger and more profound discoveries in the decades to come. But for now, the key insight was this. Emptiness was not what we thought it was. The space between solar systems was not a void. It was a medium, a substance, a part of the galaxy's living structure, and understanding it would be the key to understanding everything else. Here is the paradox at the heart of the interstellar medium. It is almost nothing, yet it creates almost everything. Think about that for a moment. The space between stars contains roughly 1 atom per cubic centimetre. That's so sparse that if you tried to gather enough interstellar gas to fill a typical room on Earth at normal atmospheric density, you'd need to sweep up a volume larger than the entire solar system. It's barely there. It's a whisper of matter in an ocean of emptiness. And yet, from this nearly nothing, stars are born, planets form, life emerges. How is that possible? How can something so insubstantial give rise to something so substantial? This is the contradiction that puzzled astronomers for decades, and solving it required a complete rethinking of how matter behaves on cosmic scales. The key lies in time and gravity. Individually, the atoms in the interstellar medium are insignificant. A single hydrogen atom drifting through space has almost no gravitational pull. It exerts no force on anything around it. It's powerless. But when you have trillions upon trillions of those atoms spread across light years of space, something changes. Collectively, they have mass, and mass creates gravity. Gravity is patient. It works slowly, pulling atoms together atom by atom, molecule by molecule. Over hundreds of thousands of years, those atoms begin to clump. A slight overdensity in one region attracts more matter. That region grows denser, which increases its gravitational pull, which attracts even more matter. It's a runaway process, a feedback loop. The rich get richer, the dense get denser. Eventually, a cloud forms. Not a cloud like those on Earth, but a vast structure of gas and dust, hundreds of light years across, with a mass equivalent to tens of thousands of suns. These are called molecular clouds, and they are the birthplaces of stars. Inside a molecular cloud, the temperature drops. Without starlight to heat them, the atoms cool to just a few degrees above absolute zero. At these temperatures, molecules can form. Hydrogen atoms pair up into molecular hydrogen. Carbon and oxygen combine to make carbon monoxide. Nitrogen and hydrogen form ammonia. These molecules are fragile. In the heat and radiation of open space, they'd be torn apart almost instantly. But in the cold, dark interior of a molecular cloud, they're stable. The cloud continues to collapse, not all at once, but in pockets. Gravity pulls matter toward the densest regions, creating cores within the cloud. These cores are where stars will form. But before that can happen, something has to overcome the resistance of the gas. You see, as the cloud collapses, it heats up. The atoms move faster, the pressure increases. This pressure pushes outward, resisting the inward pull of gravity. For a star to form, gravity has to win. And here's where the contradiction becomes even more striking. The very thing that makes the interstellar medium so sparse, its thinness, is what allows stars to form. If space were denser, If there were more atoms per cubic centimetre, the pressure would be higher, the gas would resist collapse more strongly, stars would form less easily, or not at all. But because the interstellar medium is so thin, it has almost no pressure. When gravity starts pulling it together, there's little to stop it. Of course, it's not quite that simple. There are other forces at play. Magnetic fields thread through the interstellar medium, providing support against collapse. Turbulence, the chaotic motion of gas, stirs the clouds and prevents them from settling. Radiation from nearby stars heats the gas and drives it away. Star formation is not automatic. It requires special conditions, a delicate balance where gravity is just strong enough to overcome all the other forces. But when those conditions are met, the process is inevitable. The core of the cloud collapses, the temperature rises, atoms collide more frequently, transferring energy. The core becomes dense enough and hot enough for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. Light pours out. A star is born. And around that star, in the leftover gas and dust, planets begin to form. The dust grains collide and stick together, growing larger and larger. Over millions of years, they accumulate into planetesimals, then into protoplanets, then into full-fledged worlds. Rocky planets like Earth form close to the star, where it's warm enough to melt and differentiate the material. Gas giants form farther out, where it's cold enough for ices to condense and massive enough for gravity to capture hydrogen and helium. All of this, the star, the planets, the moons, the asteroids, comes from the interstellar medium. From that thin, almost non-existent sea of atoms, it's a transformation that seems impossible, yet it happens all the time. Right now, in the Milky Way, there are thousands of molecular clouds collapsing, thousands of new stars being born, thousands of new solar systems forming. The contradiction goes even deeper. Not only does the interstellar medium create stars, but stars create the interstellar medium. Or at least, they enrich it. You see, when the universe began, it was made almost entirely of hydrogen and helium. Those were the only elements produced in the Big Bang. But stars are forges. Inside their cores, nuclear fusion creates heavier elements: carbon, oxygen, nitrogen, silicon, iron. When a star dies, especially in a supernova explosion, it releases those elements into space. They mix with the interstellar gas, changing its composition. Over billions of years, the interstellar medium has been enriched by generations of stars. The first stars formed from pure hydrogen and helium. When they died, they left behind a trace of heavier elements. The second generation of stars formed from slightly enriched gas. When they died, the enrichment increased. This process has continued for the entire history of the galaxy. Today, the interstellar medium contains about 2% heavy elements by mass. That doesn't sound like much, but it's enough. It's enough to form rocky planets. It's enough to create the complex chemistry that leads to life. So the contradiction is this: the interstellar medium creates stars, and stars create the interstellar medium. It's a cycle, a feedback loop, a cosmic partnership. Neither can exist without the other. The emptiness gives rise to substance, and the substance returns to emptiness, over and over again. This realization changed how scientists thought about the galaxy. The Milky Way was not a static collection of stars. It was a living, evolving system. The interstellar medium was not background noise. It was the engine that drove galactic evolution. Without it, there would be no new stars. Without new stars, there would be no new planets. Without new planets, there would be no new opportunities for life. And here's the most profound part of the contradiction. You, right now, are part of this cycle. The atoms in your body were once floating in the interstellar medium. They were part of the emptiness. Over billions of years, gravity gathered them into a cloud. That cloud collapsed into a star. That star created heavier elements. Eventually, those elements found their way into a rocky planet, into an ocean, into a living cell, into you. Emptiness created you, not in a poetic sense, but in a literal, physical sense. The space between stars is where your atoms came from, and when you die, when the Earth is eventually consumed by the sun's expansion, those atoms will return to the interstellar medium. They'll drift through space again, waiting for gravity to pull them into the next generation of stars and planets. The contradiction is not really a contradiction at all. It's a cycle. It's the way the universe works. Emptiness and substance are not opposites. They're phases of the same process. The interstellar medium is both the beginning and the end, the source and the destination. It's the quiet sea from which everything emerges and to which everything returns. And that changes everything. It means the space between stars is not lifeless. It's pregnant with potential. It means emptiness is not absence. It's possibility. It means that even in the darkest, coldest, loneliest regions of the galaxy, creation is waiting to happen. This is the contradiction. This is the truth. The thinnest substance in the universe is also the most creative. The emptiest space is also the fullest. And understanding this is the first step toward understanding how the galaxy, and everything in it, came to be. Once astronomers accepted that the interstellar medium existed, the next question became urgent. What, exactly, was it made of? The observations showed gas and dust, but the details were murky. How much of each? What were their temperatures? How were they distributed? And perhaps most importantly, was there anything else out there? Something they hadn't detected yet. Different groups of scientists proposed different answers, and for decades, competing theories about the nature of the interstellar medium shaped the field of astronomy. Some believed it was mostly cold, neutral hydrogen. Others argued it was primarily hot, ionized plasma. Still others suggested that magnetic fields and cosmic rays played a dominant role. The debates were intense, sometimes contentious, because the answer would determine how they understood the galaxy itself. The first major theory focused on neutral hydrogen. In the 1940s and 50s, radio astronomers discovered that hydrogen atoms emit a specific wavelength of radio waves, about 21 centimeters, when the spin of the electron flips relative to the proton. This emission was incredibly useful because radio waves pass through dust without being absorbed. For the first time, astronomers could map the distribution of hydrogen throughout the galaxy, even in regions obscured by dust. What they found was remarkable. Hydrogen was everywhere. It filled the space between stars in vast clouds and filaments. Some regions were dense, with hundreds of atoms per cubic centimetre. Others were sparse, with less than one atom per cubic centimetre. But on average, the galaxy was permeated by a thin layer of neutral hydrogen, concentrated in the galactic disk. This led to the theory of the cold neutral medium. According to this model, most of the interstellar medium consisted of hydrogen atoms at temperatures around 80 degrees above absolute zero. The gas was neither ionized nor molecular, just atomic hydrogen drifting through space. It was quiet, stable, and abundant. But there was a problem. Observations also showed evidence of much hotter gas. X-ray telescopes detected emissions from plasma at temperatures of millions of degrees. This hot gas was most common near regions of recent star formation, where supernova explosions had heated and ionized the surrounding material. It was also found in bubbles and cavities carved out by stellar winds from massive stars. This led to a competing theory, the hot ionized medium. Proponents argued that much of the interstellar medium was not cold and neutral, but hot and ionized. The energy from supernovae and stellar winds kept the gas heated to extreme temperatures. Even though the density was low, the high temperature meant the gas had significant pressure, which could affect the structure of the galaxy. For years, these two theories coexisted uneasily. Some astronomers favoured the cold neutral medium. Others preferred the hot ionized medium. Both sides had data to support their views, but the data didn't always agree. The problem was that the interstellar medium was not uniform, varied from place to place, and the instruments available at the time couldn't capture the full picture. Then, in the 1970s, a new idea emerged, the multi-phase model. This theory proposed that the interstellar medium wasn't a single entity, but a mixture of different phases coexisting in the same space. Just like water can exist as ice, liquid, and vapor, depending on temperature and pressure, the interstellar medium could exist in multiple states depending on local conditions. According to the multi-phase model, the interstellar medium consisted of at least three main phases. The cold neutral medium, with temperatures around 80 degrees and densities of a few tens of atoms per cubic centimetre. The warm, neutral or ionized medium, with temperatures around 8,000 degrees and densities of about 1 atom per cubic centimetre. And the hot ionized medium, with temperatures of millions of degrees and densities of 1,000th of an atom per cubic centimetre. Each phase occupied a different fraction of space. The cold medium was found in dense clouds. The warm medium filled most of the volume between clouds. The hot medium existed in bubbles and superbubbles created by supernovae. The three phases were in rough equilibrium, exchanging energy and matter through processes like heating, cooling, ionization, and recombination. The multi-phase model was revolutionary because it reconciled the conflicting observations. Both the cold and hot gas were real. They just existed in different regions, shaped by different processes. The model also explained how the interstellar medium could be both a barrier and a medium for star formation. Cold clouds could collapse to form stars, while hot bubbles could disperse gas and prevent further collapse. But even the multi-phase model left questions unanswered. For one thing, it didn't fully account for the role of magnetic fields. Observations showed that the interstellar medium was threaded with magnetic fields, which exerted forces on charged particles and influenced the flow of gas. Some scientists argued that magnetic fields were as important as temperature and density in determining the structure of the interstellar medium. Another complication was cosmic rays. These high-energy particles, mostly protons, streamed through the galaxy at nearly the speed of light. They carried energy and momentum, ionizing atoms and heating the gas. Some theories suggested that cosmic rays provided as much pressure as the thermal pressure of the gas itself, especially in regions where the density was low. And then there was the question of dark matter. By the late 20th century, astronomers had realized that most of the mass in the galaxy was invisible. It didn't emit light, didn't absorb light, and didn't interact with ordinary matter in any way they could detect. It was called dark matter, and it seemed to make up about 85% of the galaxy's total mass. Could some of that dark matter be hiding in the interstellar medium? Could there be exotic particles or structures that their instruments simply couldn't detect? These questions led to even more theories. Some scientists proposed that the interstellar medium contained primordial black holes, tiny remnants of the Big Bang that drifted through space like invisible icebergs. Others suggested that dark matter was made of weakly interacting massive particles, or WIMPs, which filled the galaxy but rarely collided with anything. Still others speculated about axions, magnetic monopoles, or other hypothetical particles. None of these theories could be confirmed or ruled out with the data available. The interstellar medium remained partially mysterious, a patchwork of known and unknown components. But the debates drove progress. Each theory motivated new observations, new instruments, new ways of looking at the galaxy. And slowly, the picture became clearer. By the early 21st century, astronomers had a reasonably complete understanding of the interstellar medium. It was a multi-phase system, with cold, warm and hot gas coexisting in dynamic equilibrium. It contained dust, molecules, magnetic fields, and cosmic rays. It was shaped by the life and death of stars, by supernovae, by stellar winds, by the slow rotation of the galaxy itself. It was complex, messy, and beautiful. But even now, mysteries remain. The exact balance between the phases is still debated. The role of magnetic fields is still not fully understood. The nature of dark matter is still unknown. And new discoveries continue to surprise us. In 2013, for example, astronomers detected a massive cloud of hot gas surrounding the Milky Way, extending far beyond the visible disk. It contains as much mass as all the stars in the galaxy combined, yet it was invisible until recently. The theories about what fills the dark are constantly evolving, refined by each new observation, each new instrument, each new insight. But the central truth remains: the space between stars is not empty. It's filled with matter and energy in forms both familiar and strange. It's a living system, constantly changing, constantly creating, constantly connecting every part of the galaxy into a single, coherent whole. This is the landscape of theories. This is the ongoing quest to understand what lies between solar systems. And the answer, as it turns out, is far richer and more complex than anyone could have imagined. Understanding the interstellar medium required more than theory. It required observation, measurement, detection. But how do you study something you can't see? How do you map an ocean of atoms so thin that a human could travel through it for years without colliding with a single particle? The investigation of the interstellar medium became one of the great technical challenges of 20th century astronomy, driving the development of new instruments, new techniques, and new ways of seeing the universe. The first tool was spectroscopy. By the early 1900s, astronomers had learned to split starlight into its component wavelengths, creating a spectrum that revealed the star's composition, temperature, and motion. But as we've seen, they also noticed absorption lines that didn't come from the stars themselves. These lines were created by gas in the space between the stars and Earth, absorbing specific wavelengths of light as it passed through. Spectroscopy became the primary method for detecting and studying the interstellar medium. By analysing absorption lines, astronomers could determine what elements were present in interstellar space, how dense the gas was, and how it was distributed along different lines of sight. They found hydrogen, helium, carbon, oxygen, and many other elements, all in varying states of ionization depending on the local temperature and radiation field. But spectroscopy had limitations. It could only detect gas that lay directly between Earth and a bright star. It couldn't map the full three-dimensional structure of the interstellar medium. and it couldn't detect neutral hydrogen, which doesn't produce strong absorption lines in visible light. The breakthrough came in 1944, when a Dutch astronomer named Hendrik van der Hulst predicted that neutral hydrogen should emit radio waves at a wavelength of 21 centimeters. This emission occurs when the electron in a hydrogen atom flips its spin relative to the proton, releasing a tiny amount of energy. The process is rare for any individual atom. It happens only once every few million years, but because there are so many hydrogen atoms in the galaxy, the cumulative emission is strong enough to detect. In 1951, 3 separate groups of astronomers detected the 21 centimeter line for the first time. It was a revolution. Suddenly, astronomers could map hydrogen throughout the galaxy, even in regions obscured by dust. Radio waves pass through dust without being absorbed, so the entire galaxy became visible. Over the following decades, radio telescopes mapped the distribution of neutral hydrogen in the Milky Way and other galaxies. They found that hydrogen was concentrated in the galactic disk, forming a thin layer that traced the spiral arms. They discovered vast clouds of hydrogen, hundreds of light years across, drifting through space. They measured the velocity of the gas using the Doppler shift of the 21 centimeter line and discovered that the galaxy was rotating, with gas in the inner regions moving faster than gas in the outer regions. Radio astronomy also revealed molecules in the interstellar medium. In 1963, astronomers detected hydroxyl, a molecule made of 1 oxygen and 1 hydrogen atom. Over the next few years, they found more molecules: water, ammonia, formaldehyde, carbon monoxide. These discoveries were shocking. Molecules were thought to be too fragile to survive in the harsh environment of space. But they were there, concentrated in cold, dense clouds where they were shielded from radiation. The detection of molecules opened up a new field: astrochemistry. Scientists began to catalogue the molecules in the interstellar medium, finding hundreds of different species. Some simple, like hydrogen cyanide, others complex, like polycyclic aromatic hydrocarbons. They studied how these molecules formed, how they interacted, and what they revealed about the physical conditions in interstellar clouds. But radio astronomy wasn't enough. To fully understand the interstellar medium, astronomers needed to observe it at other wavelengths. Infrared telescopes revealed dust, which emits thermal radiation at long wavelengths. By measuring the infrared glow from dust grains, astronomers could map the distribution of dust throughout the galaxy and estimate its temperature and composition. X-ray telescopes revealed the hot ionized medium, the million-degree gas created by supernovae and stellar winds. This gas is too hot to emit visible light or radio waves, but it glows brightly in X-rays. X-ray observations showed that the galaxy is filled with bubbles and cavities of hot gas, evidence of violent events in the recent past. Ultraviolet telescopes revealed ionized gas, atoms that have lost 1 or more electrons due to radiation from hot stars. Ultraviolet spectroscopy detected absorption lines from ionized carbon, silicon, and other elements, providing clues about the temperature and density of the warm ionized medium. Each wavelength revealed a different component of the interstellar medium. Together, they built up a comprehensive picture. The interstellar medium was not a uniform sea, but a complex, multi-phase environment. Cold molecular clouds coexisted with warm neutral gas, which in turn coexisted with hot ionized plasma. Each phase had its own properties, its own dynamics, its own role in the life of the galaxy. But the investigation didn't stop with passive observation. Astronomers also sent spacecraft into interstellar space to measure the environment directly. The Voyager probes, launched in 1977, crossed the heliopause in 2012 and 2018, becoming the first human-made objects to enter interstellar space. They carried instruments to measure the density, temperature, and composition of the interstellar plasma, providing ground truth for the remote observations. The Voyagers confirmed much of what astronomers had inferred from spectroscopy and radio observations. The interstellar medium was indeed thin, with a density of about 1/10 of an atom per cubic centimetre in the region just beyond the heliopause. The temperature was warm, around 15,000 degrees, consistent with the warm ionized medium. The magnetic field was weak, but measurable, threading through the plasma and shaping its flow. The investigation also revealed surprises. One was the discovery of interstellar clouds that were denser and cooler than expected. These clouds blocked starlight, creating dark patches in the Milky Way. Astronomers initially thought they were voids, empty regions devoid of stars, but observations in infrared and radio wavelengths showed that the clouds were actually full of gas and dust, just too cold and dense to emit visible light. Another surprise was the detection of very high-energy gamma rays from the interstellar medium. These gamma rays are produced when cosmic rays collide with atoms in the gas, creating pions that decay into photons. By mapping the gamma ray emission, astronomers could trace the distribution of cosmic rays throughout the galaxy, revealing that they are more abundant in the inner galaxy, where supernovae are more frequent. The investigation of the interstellar medium also involved computer simulations. As observational data accumulated, theorists built models to explain the structure and evolution of the interstellar medium. These models simulated the effects of gravity, pressure, magnetic fields, radiation, and turbulence, showing how gas flows, collapses, heats, and cools over time. The simulations became increasingly sophisticated, incorporating more physics and more resolution, and they helped interpret the observations, filling in gaps and testing hypotheses. By the early 21st century, the investigation had produced a detailed map of the interstellar medium in the Milky Way and other galaxies. Astronomers knew where the gas was, how much of it there was, what it was made of, and how it moved. They understood the processes that shaped it, from the slow cooling of gas in the wake of supernova to the gradual collapse of clouds under their own gravity. They had mapped the invisible ocean, charting its currents, its depths, its islands of density, and its voids of emptiness. But the investigation continues. New telescopes, like the James Webb Space Telescope, are revealing even more detail, probing deeper into molecular clouds, studying the chemistry of star-forming regions, and tracing the flow of gas in distant galaxies. The interstellar medium is not a static subject. It's constantly evolving, and our understanding of it evolves with each new observation. Mapping the invisible was one of the great achievements of modern astronomy. It showed that the space between stars is not an empty void, but a dynamic, complex environment full of structure and activity. And it revealed that understanding the interstellar medium is essential to understanding the galaxy, because the interstellar medium is where stars are born, where elements are mixed, and where the raw material for planets and life is prepared. Science is built on evidence, and the evidence for the interstellar medium came in fragments, not grand revelations, but small pieces of data accumulated over decades, each adding a little more to the picture. These fragments were mostly hidden in starlight, subtle distortions and absorptions that required careful analysis to detect. But together, they painted a detailed portrait of the invisible ocean between stars. The first fragments came from spectroscopy. When light from a distant star passes through the interstellar medium, atoms and molecules in the gas absorb specific wavelengths, creating dark lines in the star's spectrum. These absorption lines are like fingerprints, each element and molecule leaving a unique pattern. By studying these lines, astronomers could identify what was in the interstellar medium and measure its properties. One of the most important absorption lines came from sodium. In the early 20th century, astronomers noticed faint absorption lines in the spectra of binary stars that didn't move with the star's orbital motion. These lines remained fixed, indicating they were caused by gas between the stars and Earth. The wavelength of the lines matched sodium, and their narrowness indicated the gas was cold. This was some of the first direct evidence that the interstellar medium existed and had a specific temperature and composition. As spectroscopy improved, more absorption lines were discovered. Calcium, potassium, iron, titanium all left their marks in starlight. Each line revealed something about the interstellar medium. The strength of the line indicated how much of that element was present. The width of the line indicated the temperature and turbulence of the gas. The shift of the line, due to the Doppler effect, indicated how fast the gas was moving. But perhaps the most important absorption came from molecules. In the 1930s, astronomers detected absorption lines from simple molecules like CH, methylidine, and CN, cyanide radical. These discoveries were surprising because molecules were thought to be too fragile to survive in the harsh radiation environment of space. But there they were, concentrated in dense clouds where they were shielded from destructive ultraviolet light. The detection of molecules opened up a new way to study the interstellar medium. Molecules are more complex than atoms, with more energy levels and more transitions. This means they produce more absorption and emission lines, giving astronomers more information about the physical conditions in the gas. By studying molecular spectra, scientists could measure not just the composition and temperature of the interstellar medium, but also its density, pressure, and chemical reactions occurring within it. Another key fragment of data came from extinction and reddening. Astronomers noticed that distant stars appeared dimmer and redder than they should be based on their spectral type. The dimming, called extinction, was caused by dust grains in the interstellar medium absorbing and scattering light. The reddening occurred because blue light was scattered more than red light, similar to why Earth's sky is blue and sunsets are red. By measuring the amount of extinction and reddening, astronomers could estimate how much dust lay between Earth and a given star. They found that dust was concentrated in the galactic plane, forming a thin layer that obscured much of the galaxy from view. This discovery had profound implications. It meant that early maps of the Milky Way, based on visible light observations, were incomplete. Large regions of the galaxy were hidden behind dust, and their structure could only be revealed by observations at longer wavelengths, like infrared or radio. The infrared observations provided their own fragments of data. In the 1960s and 70s, astronomers launched balloons and satellites carrying infrared detectors, which revealed a warm glow from dust grains throughout the galaxy. The dust absorbed visible and ultraviolet light from stars and re-emitted it as infrared radiation. By mapping this infrared glow, astronomers could trace the distribution of dust and estimate its temperature, which ranged from about 20 to a few hundred degrees above absolute zero. Radio observations added more fragments. The 21-centimeter line from neutral hydrogen became the workhorse of interstellar medium studies. By observing this line in different directions, astronomers could map the distribution of hydrogen throughout the galaxy. They found that hydrogen was not uniform. It was clumped into clouds and filaments, with voids in between. The velocity of the hydrogen, measured from the Doppler shift of the 21-centimeter line, revealed the rotation of the galaxy and the motion of gas in the spiral arms. Radio telescopes also detected emission lines from molecules. Carbon monoxide, one of the most abundant molecules in the interstellar medium, emits a strong line at a wavelength of about 2.6 millimeters. By mapping this emission, astronomers could trace molecular clouds, the cold, dense regions where stars form. They found that molecular clouds were concentrated in the spiral arms and were closely associated with regions of active star formation. X-ray observations provided fragments about the hot component of the interstellar medium. X-ray telescopes detected diffuse emission from million-degree gas, as well as bright spots where supernova remnants and stellar winds had heated the gas to extreme temperatures. The X-ray data showed that the galaxy was filled with bubbles and superbubbles of hot plasma, evidence of multiple supernova explosions. Ultraviolet observations revealed more about the ionized gas. Ultraviolet spectroscopy detected absorption lines from ionized carbon, silicon, and other elements, showing that a significant fraction of the interstellar medium was ionized by radiation from hot stars. The ultraviolet data also revealed the presence of highly ionized species, like 5 times ionized oxygen, which could only exist in very hot gas. Each fragment of data had to be pieced together carefully. Observations at different wavelengths probed different components of the interstellar medium, and combining them required understanding how those components related to each other. It was like solving a jigsaw puzzle where the pieces came from different boxes and didn't always fit neatly together. But slowly, the picture emerged. The interstellar medium was a multi-phase environment. Cold molecular clouds, with temperatures of 10 to 20 degrees above absolute zero, and densities of hundreds to thousands of atoms per cubic centimeter. Warm, neutral and ionized gas, with temperatures of thousands of degrees and densities of about 1 atom per cubic centimeter. Hot, ionized plasma, with temperatures of millions of degrees and densities of 1,000th of an atom per cubic centimeter. And dust, tiny grains of solid material about 100th of a micron across, scattered throughout the gas. The data also revealed the dynamics of the interstellar medium. Gas was not static. It flowed, driven by pressure gradients, gravity, and the energy injected by stars. Molecular clouds collapsed to form stars. Hot bubbles expanded, driven by supernova explosions. Warm gas filled the spaces in between, acting as a reservoir that fed the molecular clouds and absorbed the energy from the hot gas. One of the most important fragments of data came from isotopes. Different isotopes of the same element have the same chemical properties but slightly different masses, which affect the wavelengths of their spectral lines. By measuring the ratios of isotopes in the interstellar medium, astronomers could trace the history of nucleosynthesis, the process by which elements are created in stars. For example, the ratio of deuterium to hydrogen in the interstellar medium is a relic of the Big Bang. Deuterium is destroyed in stars, so measuring its abundance provides information about how much gas has been processed through stars and how much remains primordial. Similarly, the ratios of carbon-12 to carbon-13 and oxygen-16 to oxygen-18 reveal the contributions of different types of stars to the enrichment of the interstellar medium. The fragments of starlight were not just data points, they were stories. Each absorption line, each emission peak, each measurement of extinction told a story about the history and evolution of the interstellar medium. And by piecing these stories together, astronomers could reconstruct the life cycle of matter in the galaxy, from its origins in the Big Bang, through its processing in stars, to its eventual incorporation into new stars, planets, and possibly life. The data showed that the interstellar medium was not a passive backdrop. It was an active participant in the evolution of the galaxy. It regulated star formation, transported energy and matter, and connected different regions of the galaxy into a single, coherent system. Understanding the fragments of starlight was essential to understanding the galaxy as a whole. And the investigation continues. New instruments, with higher sensitivity and resolution, are revealing even finer details. Each new fragment adds to the picture, refining our understanding, challenging our theories, and opening new questions. The data is never complete, but each piece brings us closer to understanding the invisible ocean that lies between the stars. There is a truth that sits at the heart of the interstellar medium, a truth so profound that it changes everything we think we know about ourselves. It's not just that the space between stars contains matter, it's that the matter is us. Every atom in your body, every carbon, every oxygen, every nitrogen was created inside a star. Not our sun, but stars that lived and died before the solar system even existed. Those stars forged the elements in their cores through nuclear fusion, and when they died, they scattered those elements into the interstellar medium. Over millions of years, that enriched gas drifted through space until gravity gathered it into a new cloud, which collapsed to form the sun and its planets. Earth formed from that material. Life emerged from it. And now, billions of years later, you exist, made of atoms that once floated in the darkness between stars. This is not metaphor. This is documented history. Let's trace the journey of a single atom. Pick one, say a carbon atom in one of your cells. That atom began its existence about 5 billion years ago, inside a massive star located somewhere else in the galaxy. The star was much larger than the Sun, perhaps 10 or 20 times its mass. Stars like that burn fast and die young. They live for only a few million years before exhausting their fuel. Inside the star's core, temperatures reached hundreds of millions of degrees. At those temperatures, nuclear fusion occurred. Hydrogen fused into helium. Helium fused into carbon. Carbon fused into oxygen. Oxygen into neon. Neon into magnesium, and so on, building up heavier and heavier elements through a process called nucleosynthesis. Each fusion reaction released energy, which kept the star hot and prevented it from collapsing under its own gravity. But eventually, the star ran out of fuel. Without fusion to support it, the core collapsed. The collapse triggered a catastrophic explosion, a supernova, one of the most violent events in the universe. The outer layers of the star were flung into space at speeds of thousands of kilometers per second, and in the intense heat and pressure of the explosion, even heavier elements were created, elements like iron, gold, and uranium. The carbon atom we're following was part of that explosion. It was ejected into the interstellar medium along with billions of trillions of other atoms. At first, the ejected material formed a hot, expanding shell of gas, a supernova remnant, but over thousands of years, the remnant cooled and dispersed, mixing with the surrounding interstellar gas. For the next few 100 million years, the carbon atom drifted. It travelled slowly through the galaxy, carried by currents in the interstellar medium, pushed by radiation pressure from nearby stars, tugged by the weak gravitational pull of passing clouds. It collided occasionally with other atoms, sometimes forming molecules, sometimes breaking apart. It was bathed in ultraviolet light, in cosmic rays, in the faint glow of the galaxy itself. Eventually, the carbon atom found itself in a region of the galaxy where the interstellar gas was beginning to clump. Gravity was pulling gas together, forming a molecular cloud. The carbon atom became part of that cloud. Over the next million years, the cloud collapsed under its own weight. The density increased, the temperature dropped. At the center of the cloud, a new star was forming. That star would become the sun. But the carbon atom didn't end up in the sun. It remained in the disk of gas and dust that surrounded the young star, the protoplanetary disk. Within that disk, dust grains collided and stuck together, growing larger and larger. The carbon atom became part of one of those grains. Over millions of years, the grain grew into a pebble, the pebble into a boulder, the boulder into a planetesimal. Eventually, the planetesimal collided with other planetesimals, forming a protoplanet. That protoplanet became Earth. The carbon atom was now part of Earth's interior, locked in rock deep below the surface. But the story didn't end there. Over billions of years, geological processes brought the atom closer to the surface. It was released by volcanic activity, entered the atmosphere as carbon dioxide, was absorbed by a plant during photosynthesis, became part of an organic molecule, entered the food chain, and eventually found its way into a human body. Into your body. That's the journey. From a massive star, through a supernova explosion, into the interstellar medium, into a molecular cloud, into the solar system, into Earth, and finally into you. It took billions of years. It covered thousands of light years, and it's a journey shared by every atom in your body. This realization has profound implications. It means you are not separate from the cosmos. You are part of it, literally made of it. Your atoms have been recycled through multiple generations of stars. They carry the history of the galaxy written into their very nuclei. You are stardust, but more than that, you are interstellar dust. You are a product of the space between stars. Carl Sagan famously said, "We are made of star stuff." But the full truth is even more beautiful. We are made of the space between stars. We are made of the quiet, patient work of gravity and time. We are made of the ashes of ancient suns, drifting through the darkness, waiting to be gathered into new forms. And this is true not just for us, but for everything on Earth. The oxygen you breathe was created in a dying star. The calcium in your bones was forged in a supernova. The iron in your blood was synthesized in the final moments before a massive star exploded. Even the hydrogen in your body, the most common element in the universe, was created in the Big Bang and has been cycling through stars and the interstellar medium ever since. The interstellar medium is not just a physical space. It's a repository of memory. Every atom in it carries a history. Every molecule records a chapter in the story of the galaxy. When we study the composition of the interstellar medium, we're reading that history. We're uncovering the processes that shape the galaxy, the cycles of star formation and death that have been repeating for billions of years, and we're discovering our own origins. Because the same processes that created the interstellar medium also created us. The same forces that gathered gas into clouds and clouds into stars also gathered dust into planets and planets into living worlds. We are not observers standing outside the system, looking in. We are participants, products of the system, made from the same material, following the same rules. This is the deeper mystery. Not just that the interstellar medium exists, but that it connects everything. It connects stars to stars, planets to planets, life to the cosmos. It shows that the boundaries we draw between here and there, between us and them, between life and the universe, are artificial. At the atomic level, there are no boundaries. There is only the continuous flow of matter through space and time, cycling endlessly between different forms. And this flow continues. Right now, at this very moment, stars are dying and releasing their elements into the interstellar medium. Molecular clouds are collapsing to form new stars. Planets are forming around those stars. And on some of those planets, perhaps, life is emerging, made from the same cosmic recycling that made us. The atoms in your body will not stay with you forever. When you die, they will return to the Earth. Over geological timescales, they will be released back into the environment. Some will remain on Earth. Others, over billions of years, might escape into space, rejoining the interstellar medium. And then the cycle will continue. Your atoms will drift through the galaxy once more, waiting to be gathered into new clouds, new stars, new worlds. You are temporary, but your atoms are eternal. They have existed since the beginning of the universe, and they will exist until the end. They have been part of countless stars, countless planets, countless forms of matter, and you, right now, are just one chapter in their story. This is the deeper mystery. This is the connection. The interstellar medium is not out there. It's in here. It's in you. It's in everything. An understanding that changes how we see ourselves, how we see the galaxy, and how we see our place in the vast, slow cycle of cosmic existence. There was a moment in the history of astronomy when everything changed. Not because of a single observation or discovery, but because of a realization, a shift in perspective that connected all the pieces into a coherent whole. That moment came when scientists understood that the interstellar medium wasn't just a passive reservoir of gas and dust. It was part of a cycle, a grand loop that connected the birth and death of stars into a single continuous process. The cycle works like this. Stars form from the interstellar medium when gravity pulls gas together into dense clouds. Those clouds collapse, heating up until nuclear fusion ignites in their cores. A star is born. It shines for millions or billions of years, fusing hydrogen into helium, helium into carbon, and so on, creating heavier elements in its core. Eventually, the star runs out of fuel. What happens next depends on its mass. Small stars, like red dwarfs, simply fade away, cooling slowly over trillions of years. Medium stars, like the Sun, expand into red giants, shed their outer layers in a planetary nebula, and leave behind a white dwarf. Massive stars, more than 8 times the mass of the Sun, explode in supernovae, leaving behind neutron stars or black holes. But in all cases, except for the smallest stars that haven't yet had time to die, the star returns material to the interstellar medium. Planetary nebulae release gently expanding shells of gas. Supernovae blast material outward at thousands of kilometers per second. Stellar winds from massive stars blow bubbles in the surrounding gas. All of this material, enriched with the heavy elements created by fusion, mixes with the existing interstellar medium. That enriched gas then drifts through space. It cools, it disperses, it mixes with other gas. Over millions of years, it becomes part of the general background of the interstellar medium, indistinguishable from the gas that was already there. But it's not the same. It's been processed. It's been changed. It now contains elements that didn't exist before. Carbon, oxygen, iron, all the building blocks of rocky planets and life. Eventually, gravity pulls some of that gas together again. A new molecular cloud forms. That cloud collapses. A new generation of stars is born, and the cycle continues. Birth, life, death, rebirth, over and over, for billions of years, across the entire galaxy. This realization that stars and the interstellar medium are part of a continuous cycle was the turning point. It transformed how astronomers understood the galaxy. The Milky Way was not a static collection of stars that had been there since the beginning. It was a dynamic, evolving system. Stars were constantly being born and dying. The composition of the interstellar medium was constantly changing, as each generation of stars added more heavy elements. The galaxy was alive, in a sense, constantly recycling its material, constantly creating new structures. The evidence for this cycle came from multiple sources. One was the observation that different stars had different compositions. Older stars, formed billions of years ago, had fewer heavy elements. Younger stars, formed more recently, had more. This made sense if heavy elements were being created and released by stars over time. Each generation inherited the enrichment from previous generations. Another piece of evidence came from the distribution of elements in the interstellar medium. Astronomers found that regions with recent star formation had higher abundances of elements like oxygen and nitrogen, consistent with them being enriched by supernova explosions. Regions far from recent star formation had lower abundances, consistent with less enrichment. But perhaps the most convincing evidence came from isotopes. Radioactive isotopes, created in supernova explosions, have been found in meteorites that formed in the early solar system. These isotopes have short half-lives, meaning they decay quickly. The only way they could have been present when the solar system formed is if a supernova exploded nearby just before or during the collapse of the molecular cloud that gave birth to the sun. This showed that the cycle was real, that stars were constantly dying and enriching the gas from which new stars formed. The turning point was not just scientific, it was philosophical. It showed that the universe was not made of separate, isolated parts. Everything was connected. The atoms in your body were created in stars that died long before the sun existed. Those atoms drifted through the interstellar medium, were incorporated into a new molecular cloud, formed the Earth, and eventually became part of you. You are not separate from the cosmos. You are part of the cycle. This understanding also had practical implications. It meant that the composition of the interstellar medium was not uniform across time or space. In the early universe, shortly after the Big Bang, there were no heavy elements. The first stars formed from pure hydrogen and helium. When those stars died, they enriched the interstellar medium with the first heavy elements. The second generation of stars formed from slightly enriched gas, and so on, generation after generation, until today, when the interstellar medium contains about 2% heavy elements by mass. This gradual enrichment is called chemical evolution, and it's one of the key processes that shaped the galaxy. Without it, there would be no rocky planets. Without rocky planets, there would be no life. The cycle of star formation and death is not just an abstract process. It's the mechanism that created the conditions for life to exist. The turning point also revealed the timescales involved. The cycle operates on scales of millions and billions of years. A massive star lives for only a few million years before exploding. The gas from that explosion takes millions of years to mix with the interstellar medium. The formation of a new molecular cloud takes tens of millions of years. The collapse of that cloud into stars takes another million years, and then the cycle begins again. From a human perspective, these timescales are incomprehensible, but from a galactic perspective, they're the natural rhythm. The galaxy breathes slowly, inhaling dead stars and exhaling new ones. And we are living in the middle of one of those breaths. The life cycle revealed something else. The role of feedback. Stars don't just form passively from the interstellar medium, they actively shape it. Massive stars emit powerful winds that blow bubbles in the gas, clearing out regions and compressing the surrounding material. Supernovae inject enormous amounts of energy, heating the gas to millions of degrees and creating shock waves that travel for thousands of light years. These processes regulate star formation, preventing the galaxy from forming stars too quickly and using up all its gas in a single burst. Feedback creates a balance. Gas collapses to form stars. Stars heat and disperse the gas. The gas cools and collapses again. This balance is why the Milky Way has been forming stars steadily for billions of years, rather than forming all its stars at once and then going dark. The turning point also connected the interstellar medium to the larger structure of the galaxy. The spiral arms, the bright bands of stars and gas that wind through the Milky Way, are not permanent structures. They're density waves, regions where gas piles up temporarily before passing through. When gas enters a spiral arm, it's compressed, triggering star formation. The newly formed massive stars illuminate the spiral arm, making it visible. But the stars don't stay in the spiral arm. They drift out, and the spiral arm moves on to compress new gas. The interstellar medium is the medium through which the spiral pattern propagates. Understanding the life cycle also revealed the fate of the galaxy. Right now, the Milky Way still has plenty of gas to form stars. But eventually, billions of years from now, that gas will be used up. Star formation will slow, then stop. The galaxy will fade as its stars age and die. Unless new gas is acquired through mergers with other galaxies or accretion from the intergalactic medium, the Milky Way will eventually become a graveyard of dead stars with no new births to replace them. But that's far in the future. For now, the cycle continues. Stars are born, stars die, and the interstellar medium connects them. It's a cycle that has been operating for the entire history of the galaxy, and it will continue for billions of years to come. The turning point was realizing that we are part of that cycle, that our existence depends on it, and that understanding it is essential to understanding ourselves. This was the paradigm shift. This was the moment when the interstellar medium stopped being a curiosity and became central to our understanding of the galaxy. It was the thread that tied everything together, the link between past and future, between death and birth, between stars and life. And it changed everything. Once the life cycle of the interstellar medium was understood, the consequences became clear. The galaxy was not a machine running down, slowly using up its fuel until it died. It was an ecosystem, a system that recycled its material, that adapted and evolved over time. And this recycling had profound effects on everything, from the composition of stars to the possibility of life. The first consequence was elemental abundance. When the universe began, it was made almost entirely of hydrogen and helium, the two lightest elements. These were created in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. But heavier elements, the carbon, oxygen, nitrogen, and iron that make up planets and living things, did not exist. They had to be created. Stars are the factories where heavy elements are made. Inside a star's core, hydrogen fuses into helium. As the star ages and the core heats up, helium fuses into carbon and oxygen. In massive stars, the process continues, creating neon, magnesium, silicon, sulfur, and eventually iron. Each fusion reaction releases energy, which keeps the star shining. But iron is the end of the line. Fusing iron requires energy rather than releasing it. So once a star's core is made of iron, fusion stops. Without fusion to support it, the core collapses. In a massive star, this collapse triggers a supernova, an explosion so violent that it briefly outshines an entire galaxy. In the intense heat and pressure of the explosion, even heavier elements are created. Elements like gold, platinum, and uranium. All of these elements are blasted into space, mixing with the interstellar medium. This is how the galaxy was enriched. The first stars, formed from pure hydrogen and helium, created the first heavy elements. When they died, they released those elements into the interstellar medium. The second generation of stars formed from gas that contained a trace of heavy elements. When they died, they added more. Generation after generation, the abundance of heavy elements increased, slowly transforming the composition of the galaxy. Today, about 2% of the interstellar medium's mass is made of elements heavier than helium. That might not sound like much, but it's enough. It's enough to form rocky planets. It's enough to create the complex molecules that life depends on. Without the recycling of material through stars and the interstellar medium, none of this would exist. The second consequence was the formation of planets. In the early universe, when the interstellar medium contained only hydrogen and helium, planets as we know them could not form. There was no solid material to build them from. But as the interstellar medium was enriched with heavy elements, conditions changed. Dust grains, made of carbon and silicon, began to form in the atmospheres of dying stars. These grains were released into the interstellar medium, where they accumulated over time. When a new star formed from this enriched gas, the dust grains in the surrounding disk collided and stuck together, growing larger and larger. Over millions of years, they formed planetesimals, then protoplanets, and finally, full-size planets. Rocky planets like Earth formed close to the star. Where it was warm, gas giants like Jupiter formed farther out, where it was cold enough for ices to condense. The presence of heavy elements also affected the chemistry of those planets. Earth's crust is made of silicon, oxygen, magnesium, and iron, all created in stars. Its atmosphere originally contained nitrogen, carbon dioxide, and water vapor, molecules made from elements forged in stellar cores. And life, when it emerged, was built from carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, all products of stellar nucleosynthesis. The third consequence was the possibility of life itself. Life, as we know it, requires a specific set of elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, often abbreviated as CHNOPS. These elements are the building blocks of proteins, DNA, and the other complex molecules that living organisms are made from. But in the early universe, most of these elements didn't exist. They had to be created in stars and distributed through the interstellar medium. The recycling of material through the galaxy was therefore a prerequisite for life. Without it, there would be no carbon to form organic molecules, no oxygen to breathe, no nitrogen to make amino acids, no phosphorus to build DNA. The cosmic recycling system, operating over billions of years, created the conditions necessary for life to emerge. But the consequences went beyond just providing the raw materials. The recycling also shaped the timing of life's emergence. The first stars formed only a few 100 million years after the Big Bang. But those stars had no planets, and even if they did, Those planets would have been made only of hydrogen and helium. It wasn't until several generations of stars had lived and died, enriching the interstellar medium, that rocky planets with the right chemistry could form. This means life, at least life like ours, could not have emerged in the very early universe. It required billions of years of stellar cycling to build up the necessary elements. Earth formed about 4.5 billion years ago, when the galaxy was already 9 billion years old. By that time, the interstellar medium had been enriched to the point where rocky planets with complex chemistry were possible. The fourth consequence was the distribution of elements across the galaxy. Because stars form, live, and die in different locations, the enrichment of the interstellar medium is not uniform. Regions with active star formation, like the spiral arms, have higher abundances of heavy elements. Regions far from recent star formation have lower abundances. This creates a gradient across the galaxy. The inner regions, where star formation has been more active, are more enriched. The outer regions, where star formation has been less active, are less enriched. This gradient affects the types of stars and planets that form in different regions. In the inner galaxy, stars are more likely to have rocky planets. In the outer galaxy, planetary systems might be dominated by gas giants or have fewer planets overall. The fifth consequence was the realization that we are part of the cycle. Every atom in your body has been recycled through the interstellar medium multiple times. Your carbon was created in one star, released in a supernova, drifted through space, became part of another star, was released again, and eventually ended up in you. Your oxygen, your nitrogen, your iron, all have similar histories. You are made of recycled stardust. This has philosophical implications. It means you are not separate from the universe. You are part of it, literally made from the same material that makes stars and planets. Your existence depends on the cosmic recycling system, on the deaths of stars that occurred billions of years ago, on the slow mixing of matter through the interstellar medium. The sixth consequence was the understanding that the cycle will continue. The sun will not shine forever. In about 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant. It will shed its outer layers, creating a planetary nebula, and leave behind a white dwarf. The material released in that nebula will mix with the interstellar medium, enriching it further. Eventually, that material will be incorporated into new stars, new planets, possibly new forms of life. Your atoms will not disappear, they will be recycled. They will become part of the interstellar medium, drift through space, and eventually be gathered into new structures. The cycle that created you will continue long after you're gone. The cosmic recycling system is one of the most important processes in the galaxy. It's the mechanism that creates diversity, that builds complexity, that makes life possible. Without it, the universe would be a simpler, less interesting place. Stars would form from pure hydrogen and helium, shine for a while, and die, leaving nothing behind. There would be no planets, no chemistry, no life. But because of recycling, the universe evolves. Each generation of stars adds to the richness of the interstellar medium. Each collapse of a molecular cloud creates new opportunities for complexity. The galaxy is not static. It's growing, changing, becoming more complex over time. And you are part of that process. Your existence is a consequence of cosmic recycling. You are made from the ashes of ancient stars, and when you're gone, your atoms will continue the journey, moving through the galaxy, waiting to be part of something new. This is the consequence of the interstellar medium. This is the legacy of the cycle. and understanding it changes everything. The discovery that the interstellar medium was part of a vast recycling system didn't just change astronomy. It changed how humanity understood its place in the universe. The impact of this realization rippled through science, philosophy, and culture, reshaping our view of origins, connections, and meaning. In science, the impact was immediate. The life cycle model became the foundation for understanding galactic evolution. Astronomers could now explain why different galaxies had different properties. Spiral galaxies, with active star formation and abundant gas, were still in the middle of their life cycle. Elliptical galaxies, with little gas and mostly old stars, had largely completed their star formation, having converted most of their gas into stars billions of years ago. The model also explained the diversity of stellar populations. Old stars, called population 2 stars, formed early in the galaxy's history from gas that contained very few heavy elements. Younger stars, called population 1 stars, formed more recently from enriched gas. By studying the composition of stars, astronomers could trace the history of the galaxy, seeing how it evolved over time. The impact extended to cosmology, the study of the universe as a whole. The recycling process meant that the universe was not just expanding and cooling, as predicted by Big Bang theory. It was also becoming more complex. The first generation of stars created the first heavy elements. Subsequent generations built on that, creating more and more elements, more and more complexity. The universe was evolving chemically, not just physically. This realization connected the history of the universe to the history of life. Life required heavy elements, which required multiple generations of stars, which required billions of years. The timeline of cosmic evolution was therefore linked to the timeline of biological evolution. You couldn't understand one without the other. In philosophy, the impact was profound. For centuries, humans had viewed themselves as separate from the cosmos. We were here, on Earth. The stars were out there, distant and unreachable. But the discovery of cosmic recycling showed that this separation was an illusion. We were made from the same material as stars. Our atoms had travelled through the galaxy before becoming part of us. We were not observers of the cosmos. We were participants. This idea that we are made of star stuff, popularized by Carl Sagan, became one of the most influential scientific concepts of the 20th century. It gave people a sense of connection to the universe, a feeling that they were part of something larger. It also provided a new perspective on mortality. Yes, individual lives are temporary, but the atoms that make us up are eternal. They existed before we were born, and they will exist after we die, continuing their journey through the cosmos. The impact also changed how we thought about the search for life beyond Earth. If the interstellar medium was enriched with heavy elements throughout the galaxy, then the conditions for forming rocky planets existed almost everywhere. And if rocky planets were common, then perhaps life was common too. The cosmic recycling system wasn't just a process that happened once on Earth. It was a universal process, operating throughout the galaxy, potentially creating countless opportunities for life to emerge. This led to renewed interest in astrobiology, the study of life in the universe. Scientists began to search for exoplanets, planets orbiting other stars, looking for worlds that might harbour life. They found thousands. Some were rocky, like Earth. Others were gas giants, like Jupiter. Many were in the habitable zone, the region around a star where liquid water could exist on a planet's surface. The cosmic recycling system had created a galaxy full of worlds. In culture, the impact was subtle but pervasive. The idea that we are made of stardust entered popular consciousness, appearing in books, movies, songs, and art. It became a way to express the connection between humanity and the cosmos, a reminder that we are not separate from nature but part of it. It also provided comfort. In a universe that could seem cold and indifferent, the idea that we are made from the same material as stars gave people a sense of belonging. The impact also extended to education. The life cycle of the interstellar medium became a standard part of astronomy courses taught to students around the world. It provided a narrative framework for understanding the galaxy, a story that connected different topics: star formation, stellar evolution, the solar system, origins of life, into a coherent whole. It showed that the universe had a history, that things changed over time, that the present was shaped by the past. But perhaps the deepest impact was on our understanding of time. The cosmic recycling system operates on scales of millions and billions of years. To understand it, you have to think in deep time, to grasp that the galaxy is old, that processes unfold slowly, that change happens gradually. This perspective was humbling. It showed that human timescales, days, years, lifetimes, are infinitesimally short compared to cosmic timescales. But it also showed that even small changes, accumulated over vast periods, can have enormous effects. The interstellar medium itself became a symbol of this deep time. It's the repository of galactic history, containing gas from the Big Bang, elements from billions of dead stars, molecules formed in cold clouds, dust grains shaped by radiation and chemistry. Every component has a history, every atom carries a story, and by studying the interstellar medium, we're reading that story, tracing the events that shaped the galaxy over billions of years. The impact also changed how we think about the future. The cosmic recycling system will continue long after we're gone. The sun will die, releasing its material into the interstellar medium. That material will drift through space, mix with other gas, and eventually form new stars. Those stars will have planets. Perhaps some of those planets will have life. The cycle will continue, generation after generation, for trillions of years. This long view of the future is both sobering and hopeful. Sobering because it reminds us that nothing is permanent, that even stars die, that the galaxy will eventually exhaust its gas and go dark. But hopeful because it shows that the cycle continues, that death leads to rebirth, that the end of one thing is the beginning of another. The echoes of the interstellar medium discovery continue to resonate. Every new observation adds to our understanding. Every new theory refines the picture. And every new generation of scientists and thinkers grapples with the implications, trying to understand what it means that we are made from the space between stars. The impact is ongoing. It's shaping how we explore the galaxy, how we search for life, how we think about our origins and our destiny. It's reminding us that we are part of a larger system, that our existence is connected to the existence of everything else, that the boundaries we draw between ourselves and the universe are artificial, and it's teaching us humility. The interstellar medium has been recycling material for billions of years. It will continue for billions more. We are a small part of that cycle, a brief moment in a process that spans the history of the galaxy, but we are part of it. And that connection, that thread linking us to the cosmos, is one of the most profound discoveries in the history of science. The echoes through time are not just scientific, they're personal. They're about understanding where you came from, what you're made of, and where you're going. And they're about finding meaning in that understanding, seeing yourself not as separate from the universe, but as an integral part of its ongoing story. Behind every discovery about the interstellar medium, behind every observation and theory, were people. Dreamers who looked at the night sky and wondered what lay between the stars. Scientists who spent their careers analysing spectra, measuring absorption lines, building instruments to detect the invisible. Engineers who designed telescopes and spacecraft to explore the boundaries of our solar system. These are the human stories that drove our understanding of the space between stars. One of the earliest dreamers was Johannes Hartmann, the German astronomer who in 1904 detected the first evidence of interstellar gas. Hartmann was studying binary stars, systems where two stars orbit each other. He noticed absorption lines in the spectrum of Delta Orionis that didn't shift with the star's motion. This was strange. If the lines came from the stars, they should move as the stars orbited, but they didn't. They stayed fixed. Hartmann realized that the gas causing these absorption lines wasn't in the stars. It was between the stars and Earth. It was the first direct evidence that interstellar space contained matter. But Hartmann didn't fully appreciate the significance of his discovery. He published his findings in a brief paper and moved on, and to other research. It would be years before others recognized the importance of what he'd found. Another key figure was Hendrik van der Hulst, the Dutch astronomer who predicted the 21-centimetre emission line from neutral hydrogen. During World War II, the Netherlands was occupied by Nazi Germany. Universities were closed, scientific work was disrupted, and many astronomers were forced to hide or flee. Van der Hulst continued his research in secret, working on theoretical problems that didn't require observations. One of those problems was whether hydrogen in interstellar space would emit radio waves. In 1944, van der Hulst calculated that it should. When the electron in a hydrogen atom flips its spin, it releases a tiny amount of energy at a wavelength of 21 centimeters. The process is extremely rare for any individual atom, but with enough hydrogen in the galaxy, the cumulative emission should be detectable. After the war, van der Hulst published his prediction, and in 1951, 3 independent groups detected the 21 centimeter line. It transformed radio astronomy and opened up a new way to study the interstellar medium. Van der Hulst's story is a reminder that science continues even in the darkest times. That curiosity and the desire to understand the universe can persist even when the world is falling apart. His prediction, made during wartime, became one of the most important tools for mapping the galaxy. Then there were the radio astronomers who built the instruments to detect the 21 centimeter line. Harold Ewan and Edward Purcell at Harvard. C. Alex Muller and Jan Oort in the Netherlands, and Frank Kerr and Paul Wild in Australia, all working independently, racing to be the first to confirm van der Hulst's prediction. When they succeeded, they opened a window into the invisible ocean of hydrogen that fills the galaxy. Jan Oort, in particular, dedicated much of his career to understanding the structure of the Milky Way. Using radio observations of hydrogen, he mapped the galaxy's spiral arms, showing that they were concentrations of gas and young stars. He also studied the rotation of the galaxy. Measuring how fast different regions were moving, his work provided some of the first evidence for dark matter, showing that the galaxy's rotation couldn't be explained by the visible stars and gas alone. Something else, something invisible, was providing additional gravitational pull. Another dreamer was Lyman Spitzer, an American astrophysicist who pioneered the study of the interstellar medium's physical properties. In the 1940s and 50s, Spitzer developed models of how gas in the interstellar medium was heated and cooled, how it was ionized by radiation from stars, and how it interacted with magnetic fields. He showed that the interstellar medium wasn't a simple, uniform sea, but a complex, multi-phase environment with cold clouds, warm gas, and hot bubbles coexisting in the same space. Spitzer also championed the idea of space telescopes, instruments placed above Earth's atmosphere that could observe wavelengths of light blocked by the air. He spent decades advocating for what would eventually become the Hubble Space Telescope, launched in 1990. Hubble revolutionized astronomy, providing stunning images and precise measurements of the universe. It also contributed to our understanding of the interstellar medium, observing absorption lines in ultraviolet light that revealed the composition and distribution of gas in the galaxy. And then there are the engineers and mission planners behind the Voyager spacecraft. Launched in 1977, Voyager 1 and 2 were designed to explore the outer planets. But after completing their primary missions, they continued outward, heading toward the edge of the solar system and beyond. The decision to keep the Voyagers operating, even as they left the planets behind, was not obvious. It required resources, funding, and commitment from NASA and the scientific community. But the Voyagers rewarded that commitment. In 2012 and 2018, they crossed the heliopause and entered interstellar space, becoming the first human-made objects to do so. The data they sent back confirmed much of what astronomers had predicted about the interstellar medium, but also revealed surprises, unexpected structures in the boundary between solar and interstellar space, variations in the density and temperature of the plasma. The Voyagers are still out there, still sending signals back to Earth, though their power is fading and their instruments are shutting down one by one. They're more than 20 billion kilometers away, farther from home than anything humanity has ever created. And they carry with them golden records, messages from Earth, intended for any intelligent beings who might find them in the distant future. The Voyagers are not just scientific instruments. They're ambassadors, carrying humanity's dreams into the space between stars. These are just a few of the people who contributed to our understanding of the interstellar medium. There are many more: astronomers, physicists, engineers, mathematicians, each adding a piece to the puzzle. Some are famous, others are forgotten, but all were driven by the same curiosity, the same desire to understand what lies between the stars. The human element is important because it reminds us that science is not just about data and theories. It's about people, about their dreams, their struggles, their persistence. It's about individuals who spent years, sometimes entire careers, working on problems that might not be solved in their lifetimes. It's about the slow, patient accumulation of knowledge, built up over generations, with each generation standing on the shoulders of those who came before. And it's about wonder. Every scientist who studied the interstellar medium was driven, at some level, by a sense of awe at the universe. They looked at the night sky and saw not just stars, but questions. What lies between them? What is space made of? How do stars form? How did we come to be? These questions are not just scientific. They're human. They're about our place in the cosmos, about where we came from and where we're going. The dreamers who studied the interstellar medium also faced challenges: limited funding, skeptical colleagues, technological constraints. Hartmann's discovery was largely ignored for years. Van der Hulst made his prediction during wartime, when scientific collaboration was nearly impossible. The Voyagers were launched with uncertain prospects, and many doubted they would reach interstellar space. But the dreamers persisted. They believed that understanding the space between stars was worth the effort. And they were right. The knowledge we've gained about the interstellar medium has transformed our understanding of the galaxy. It's shown us that the space between stars is not empty, but full of history, full of potential. It's revealed the cycle of stellar birth and death, the enrichment of the galaxy with heavy elements, the origins of the atoms that make up planets and life. It's connected us to the cosmos in ways that earlier generations could hardly have imagined. The human element is ongoing. Right now, scientists are continuing to study the interstellar medium, using new instruments, developing new theories, making new discoveries. The James Webb Space Telescope is probing molecular clouds where stars are forming. Radio telescopes are mapping the distribution of gas in distant galaxies. Computer simulations are modeling the complex interactions between gas, stars, magnetic fields, and dark matter. And there will be new dreamers, new generations of scientists who look at the night sky and wonder, who ask questions that haven't been asked before, who develop tools that don't yet exist, who discover things we can't yet imagine. The exploration of the Dalder's interstellar medium is not finished. It's ongoing, a continuous human endeavour that spans lifetimes, generations, and centuries. Because ultimately, the interstellar medium is not just about space. It's about us. It's about understanding where we came from, what we're made of, and how we fit into the larger story of the cosmos. And that's a question that will continue to drive human curiosity for as long as we exist. For all the progress in understanding the interstellar medium, there remains a fundamental challenge, a barrier that has frustrated scientists and dreamers for generations. The distances are too vast. The timescales are too long. The silence between stars is not just a physical reality. It's a practical limit on what we can do, on where we can go, on how we can explore. The nearest star to our Sun, Proxima Centauri, lies about 4.2 light-years away. That's roughly 40 trillion kilometers. To put that in perspective, the Voyager 1 spacecraft, the fastest and most distant human-made object, has been travelling for over 40 years and has covered only about 20 billion kilometers. At its current speed, it would take Voyager over 70,000 years to reach Proxima Centauri, and that's assuming it were heading in that direction, which it's not. This is the first opposition. Distance. The space between stars is so vast that even travelling at incredible speeds, far faster than anything we've achieved, interstellar journeys would take decades, centuries, or millennia. With our current technology, the stars are effectively unreachable. There have been proposals, of course. Some scientists have suggested building spacecraft that could travel at a significant fraction of the speed of light, perhaps 10 or 20%. At those speeds, a trip to Proxima Centauri might take only a few decades. But achieving such speeds would require enormous amounts of energy, far more than any propulsion system we've developed. It would also require solving problems of shielding, because even the thin interstellar medium becomes dangerous when you're travelling that fast. Collisions with individual atoms, harmless at low speeds, would release enough energy to damage or destroy a spacecraft at relativistic velocities. Others have proposed generation ships, massive spacecraft that would travel for centuries, with multiple generations of humans living and dying aboard before reaching their destination. But this raises profound ethical and practical questions. How do you ensure the ship remains functional for centuries? How do you maintain a stable society in such a confined, isolated environment? And how do you preserve the mission's purpose across generations who never knew Earth and might not care about reaching a distant star? Then there are more speculative ideas, warp drives that bend space, wormholes that connect distant points, suspended animation that lets travellers sleep through the journey. But these remain firmly in the realm of science fiction. We have no evidence that such technologies are possible, and even if they are, we have no idea how to build them. The second opposition is isolation. Interstellar space is empty in a way that's hard to comprehend. The nearest stars are separated by light years of near vacuum. If you were drifting in interstellar space, far from any star, you would be surrounded by darkness. The stars would be distant points of light, cold and unreachable. You would be alone in a way that no human has ever been alone, cut off from any source of energy, any hope of rescue, any connection to home. This isolation is not just physical, it's also informational. Light from the nearest star takes over 4 years to reach us. That means if we sent a message to a planet orbiting Proxima Centauri, we'd wait over 8 years for a reply. 4 years for the message to get there and 4 years for the response to come back. A conversation would be impossible. Even if we found evidence of life, which on a planet around Proxima Centauri, we couldn't interact with it in any meaningful way within a human lifetime. The third opposition is energy. The interstellar medium is cold, just a few degrees above absolute zero in most regions. It contains almost no thermal energy that could be harnessed. There's no air to breathe, no water to drink, no resources to exploit. A spacecraft travelling through interstellar space would have to carry all its energy with it, or harvest it from the faint radiation of distant stars. But that radiation is weak, spread thin across the vast emptiness. Solar panels that work near Earth would produce almost nothing in interstellar space. This creates a paradox. To reach the stars, you need enormous amounts of energy. But once you're in interstellar space, energy is scarce. You're crossing a desert where there's no food, no water, no shelter. And the crossing takes not days or weeks, but decades or centuries. The fourth opposition is silence. The interstellar medium is not just physically empty, it's also informationally quiet. There's no communication infrastructure, no relay stations, no network connecting distant stars. Once a spacecraft leaves the solar system, it's on its own. It can send signals back to Earth, but those signals grow weaker with distance, eventually fading into noise. The Voyagers are still transmitting, but their signals are so faint that they require massive radio antennas to detect. And as they drift farther away, even those signals will become undetectable. This silence is profound. It means that exploration of the interstellar medium is one way. Once a spacecraft crosses the heliopause, we might receive data from it for a while, but eventually it will pass beyond our ability to communicate. It will become a silent traveller, drifting through the galaxy with no connection to its creators. Some scientists have argued that this is the ultimate barrier to interstellar exploration, not just the distance or the energy, but the silence. The inability to maintain contact, to guide the mission, to receive updates or send corrections. A spacecraft sent to another star would have to be completely autonomous, capable of making decisions, adapting to unexpected situations, and completing its mission without any input from Earth. We don't yet have the artificial intelligence to build such a spacecraft. The fifth opposition is time. Even if we solved all the technical challenges, even if we built a spacecraft that could travel at a significant fraction of the speed of light, the timescales involved would still be a barrier. A journey to the nearest star would take decades, to more distant stars, centuries. And during that time, everything would change. The people who built the spacecraft would age and die. The technology that launched it would become obsolete. The civilization that sent it might collapse or transform beyond recognition. This creates a strange disconnect. The spacecraft would be a relic of the past, carrying the technology and knowledge of a bygone era, arriving at a destination where it might no longer be relevant, and any discoveries it made would take years or decades to transmit back, by which time they might no longer matter. Despite all these oppositions, humans continue to dream of crossing the silence between stars. We send spacecraft to the edge of the solar system and beyond. We search for exoplanets, cataloguing worlds that orbit other stars. We listen for signals from extraterrestrial civilizations, hoping to find that we're not alone in the galaxy. We develop new propulsion concepts, new materials, new ways of thinking about the problem. But the silence remains. The interstellar medium is a barrier, not because it's hostile, but because it's empty. It's the distance made manifest, the vast stretches of near nothing that separate solar systems. And crossing it requires more than technology. It requires a fundamental shift in how we think about exploration, about time, about our place in the galaxy. The opposition is real, but it's also a challenge, a problem waiting to be solved. And throughout history, humans have been remarkably good at solving seemingly impossible problems. We've crossed oceans, climbed mountains, flown through the air, and walked on the moon. The silence between stars is the next frontier, the next barrier to overcome. Whether we'll succeed remains to be seen, but the dream persists. The silence calls to us, and we continue to answer, sending our machines, our messages, our hopes into the void between stars, hoping that someday, somehow, we'll find a way to bridge the gap. There comes a moment in the study of the interstellar medium when the intellectual understanding transforms into something deeper, when the facts, the data, the theories coalesce into a realization that is not just scientific but personal, almost spiritual. That moment is the awakening, when you truly grasp that you are made of stardust. It's easy to say the words, we are made of star stuff. The atoms in our bodies were forged in the cores of ancient stars. We've heard this before. It's become almost cliché, repeated so often that it's lost some of its impact. But when you really sit with the idea, when you trace the journey of a single atom from a star's core through a supernova, into the interstellar medium, into a molecular cloud, into the solar system, into Earth, into a living cell, into you, the weight of it becomes overwhelming. You are not separate from the cosmos. You are part of it, not in a metaphorical sense, but in a literal, physical, provable sense. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of it came from the space between stars. You are made of the interstellar medium, concentrated and organized into a living form. You are the universe experiencing itself. This awakening changes everything. It changes how you see the night sky. Those stars are not distant, unreachable objects. They're relatives, siblings in a cosmic family. The atoms in your body and the atoms in those stars came from the same source, were created by the same processes, are part of the same cycle. When you look up at the stars, you're looking at home, at the place your atoms came from, and the place they'll return to. It changes how you see death. Yes, your body will die. The pattern that is you, the specific arrangement of atoms that creates consciousness and memory and personality, will cease. But the atoms themselves will not disappear. They'll return to the Earth, be dispersed into the environment, and over vast timescales, some of them will escape back into space, back into the interstellar medium. They'll drift through the galaxy once more, waiting to be part of the next cycle. Death is not an ending. It's a return, a completion of the loop. It changes how you see life. Life is not an accident, not a fluke, not a random occurrence in an otherwise dead universe. Life is a consequence of the cosmic recycling system, a natural outcome of billions of years of stellar evolution. The elements that make you up were created specifically through processes that occur in stars. The conditions that allowed life to emerge on Earth were prepared by countless generations of stars that lived and died before the sun existed. You are here because the universe made you, through the slow, patient work of gravity, fusion, and time. It changes how you see connections. You are not an isolated individual. You are made of the same material as everything else. The atoms in your body were once in other living things, other planets, other stars. They've been recycled countless times, taking countless forms. You share atoms with trees, with oceans, with mountains, with every person who has ever lived. You are connected to everything at the most fundamental level. The awakening also brings a sense of scale, both humbling and empowering. Humbling because it reminds you how small you are. You're a brief arrangement of atoms on a small planet orbiting an ordinary star in the suburbs of a galaxy that contains hundreds of billions of stars. Your lifetime is a flash compared to the age of the universe. You're insignificant in the grand scheme of cosmic events, but also empowering because it reminds you what you're made of. You're built from the cores of stars. The atoms in your body required billions of years and extreme conditions to create. You're made of elements forged in supernova explosions, events so violent they briefly outshine entire galaxies. You're a product of the universe at its most creative and most destructive. You're rare, complex, and precious. The awakening brings responsibility too. If you're part of the cosmic cycle, if your atoms came from the interstellar medium and will return to it, then you're a steward of that material, however briefly. What you do with those atoms matters. How you live, how you treat others, how you engage with the world. It's all part of the larger story of those atoms, part of their journey through time. Some people find this awakening frightening. It can be unsettling to realize that you're not permanent, that you're just a temporary configuration of atoms that will eventually disperse. It can feel nihilistic, as if your existence doesn't matter because you're just a brief eddy in the flow of matter through the universe. But others find it comforting. It means you're part of something larger, something that predates you and will outlast you. It means your atoms have a history and a future that extends far beyond your individual life. It means you're connected to everything, that you're not alone, that you're part of the grand story of the cosmos. The awakening also changes how you think about the search for life beyond Earth. If we are made of stardust, if we are products of the cosmic recycling system, then the same processes that created us are happening throughout the galaxy. Wherever there are stars, there is nucleosynthesis. Wherever stars die, there is enrichment of the interstellar medium. Wherever molecular clouds collapse, there is the potential for new solar systems, new planets, new opportunities for life. We are probably not unique. We might not even be rare. Life might be a natural consequence of the universe's chemistry and physics, something that emerges wherever conditions allow. And if that's true, then the galaxy might be full of other beings who have had their own awakenings, who have realized that they too are made of stardust, that they too are part of the cosmic cycle. This idea that we are not alone, that we might be part of a community of living worlds scattered across the galaxy, is both exciting and humbling. It means we have companions, even if we haven't met them yet. It means the universe is richer and more interesting than a cold, dead expanse. It means the cycle of stellar birth and death has given rise not just to us, but potentially to countless other forms of life, each unique, each exploring their own corner of the cosmos. The awakening is not a one-time event, it's a process, a deepening understanding that continues throughout life. Each time you look up at the stars, each time you learn something new about the universe, each time you ponder your place in it, the awakening deepens. You see new connections, new implications, new meanings, and the awakening is personal. For some, it leads to a sense of awe and wonder at the beauty of the universe. For others, it leads to questions about purpose and meaning. For still others, it leads to a commitment to protect and preserve the Earth, this rare and precious world where the atoms of the universe have organized themselves into living forms. But whatever form it takes, the awakening is transformative. It's the moment when you stop seeing yourself as separate from the universe and start seeing yourself as part of it. It's when you realize that the space between stars is not out there, but here, in you. It's when you understand that the interstellar medium is not just a scientific topic, but a mirror, reflecting back the truth of what you are and where you came from. We are stardust. We are the universe made conscious. We are atoms that have travelled billions of light years and billions of years through time to be here, now, briefly aware of themselves before continuing their journey. That is the awakening. And once you've had it, you can never see the universe, or yourself, the same way again. After all the data, all the theories, all the understanding of the interstellar medium, there remains one final revelation that brings everything together. It's a truth so simple, yet so profound, that it redefines how we see the Milky Way itself. The galaxy breathes, not in the way living things breathe, with lungs and air, but in a cosmic sense, the galaxy inhales and exhales. It draws matter in and expels it. It cycles energy and material through different states, different phases, different forms, and the space between stars. The interstellar medium is the mechanism of that breath. The inhale happens when molecular clouds collapse. Gravity pulls gas together, concentrating it, compressing it, until it's dense enough to form stars. This is the galaxy gathering itself, pulling material from the diffuse interstellar medium into compact objects. Matter that was spread across light years becomes concentrated into stellar cores where nuclear fusion ignites. The galaxy inhales, drawing in its breath. The exhale happens when stars die. Small stars shed their outer layers gently, creating planetary nebulae that expand slowly into space. Massive stars explode in supernovae, blasting material outward at thousands of kilometers per second. Stellar winds from hot, young stars blow bubbles in the surrounding gas, pushing it away. All of this is the galaxy expelling matter back into the interstellar medium, dispersing what was once concentrated. The galaxy exhales, releasing its breath. And then the cycle repeats. The expelled material mixes with the existing interstellar medium, cools, drifts, and eventually collapses again to form new stars. Inhale, exhale, inhale, exhale. The rhythm is slow, measured in millions of years per breath, but it's steady, constant, and it's been happening for the entire history of the galaxy. This breathing is not just a metaphor. It's a physical process that shapes the structure and evolution of the Milky Way. The spiral arms, the bright bands of stars that wind through the galaxy, are manifestations of this breath. Gas piles up in the spiral arms, compressed by density waves, triggering star formation. That's the inhale. The newly formed massive stars then heat and disperse the gas, pushing it out of the spiral arms. That's the exhale. The breathing also creates the multi-phase structure of the interstellar medium. Cold molecular clouds are regions where the galaxy has inhaled deeply, concentrating matter. Hot ionized bubbles are regions where the galaxy has exhaled forcefully, dispersing matter. Warm, neutral gas is the intermediate state, the space between breaths, where matter is transitioning from one phase to another. And the breathing is self-regulating. If too many stars form, they inject too much energy into the interstellar medium, heating it and preventing further collapse. Star formation slows down. The galaxy pauses its inhale. If too few stars form, the gas cools and accumulates, increasing the likelihood of collapse. Star formation picks up again. The galaxy resumes its breath. This feedback keeps the galaxy in balance, preventing it from forming all its stars at once or shutting down completely. The revelation is that the Milky Way is not a static structure. It's a living system, not in a biological sense, but in a dynamic sense. It has processes that regulate themselves, cycles that sustain themselves, a rhythm that continues over cosmic time. The interstellar medium is not just space between stars. It's the lungs of the galaxy, the medium through which the galaxy breathes, the mechanism that keeps it alive. This changes how we see galactic evolution. The Milky Way didn't form all at once and then remain unchanged. It's been evolving, breathing, cycling its material for billions of years. Each breath changes it slightly. Each generation of stars enriches the interstellar medium with more heavy elements. Each supernova creates more complex chemistry. Over time, the galaxy becomes more complex, more enriched, more capable of forming rocky planets and life. The breathing also connects the small scale to the large scale. The life cycle of a single star, its birth, life, and death, is part of the galaxy's larger breath. You can't understand one without the other. Stars don't exist in isolation. They're part of the galactic respiratory system, drawing from the interstellar medium and returning to it. And the breathing connects the past to the future. The gas that's collapsing to form stars right now came from stars that died millions of years ago. The elements in those new stars will eventually be returned to the interstellar medium, where they'll wait for the next collapse, the next generation. The breath connects every era of the galaxy's history into a continuous cycle. The revelation also has implications for other galaxies. The Milky Way is not unique. Every spiral galaxy breathes in a similar way. Some breathe faster, with more active star formation and more frequent supernovae. Others breathe more slowly, with less activity and longer cycles. Elliptical galaxies have largely stopped breathing. They've used up most of their gas and are no longer forming significant numbers of stars. They're holding their breath, waiting, but the Milky Way is still breathing. Right now, at this moment, molecular clouds are collapsing somewhere in the galaxy, forming new stars, and somewhere else, stars are dying, expelling their material back into space. The galaxy is inhaling and exhaling simultaneously, different regions at different phases of the cycle. The breath is not synchronized, it's distributed, happening everywhere at once, creating the complex dynamic structure we observe. The breathing also explains some mysteries. For example, the disk of the Milky Way is thin, only about 1,000 light-years thick, but tens of thousands of light-years across. Why? Because of the breathing. Gas is constantly being dispersed by supernova explosions and stellar winds, which push it out of the disk. But gravity pulls it back down. The equilibrium between vertical dispersion and gravitational collapse creates the thin disk structure. The galaxy's breath shapes its form. Another mystery is the rate of star formation. The Milky Way forms about 1 to 2 solar masses of new stars per year. That might not sound like much, but it's been sustained for billions of years. How? because of the self-regulating nature of the breath. Too much star formation triggers feedback that slows it down. Too little allows gas to accumulate and triggers more. The rate is balanced, maintained by the respiratory cycle. The revelation of the galaxy's breath also brings a sense of perspective. We are living during one moment of one breath in a cycle that's been continuing for over 13 billion years. The Milky Way has taken billions of breaths since it formed, and it will take billions more before it finally goes silent. Our entire recorded history, all of human civilization, fits into a tiny fraction of one of those breaths. But we are part of it. Our sun formed from one of the galaxy's inhales. It will eventually contribute to one of the galaxy's exhales. The atoms in our bodies have been through this cycle multiple times, created in the exhale of one breath, incorporated into the inhale of another. We are not observing the breath from outside, we are part of the breath itself. The galaxy breathes, and we are part of that breath. The space between stars is where the breathing happens, where matter transitions from concentrated to dispersed and back again. Understanding this is understanding the galaxy at its most fundamental level. It's seeing the Milky Way not as a collection of separate objects, but as a single, integrated system, a cosmic organism that has been alive for billions of years and will continue for billions more. This is the deepest revelation. This is the ultimate truth about the interstellar medium. It's not empty space. It's not a void. It's the medium of the galaxy's breath, the mechanism through which the Milky Way lives. And recognizing this changes everything, because it shows that we are not separate from the galaxy. We are part of its breathing, part of its life, part of its ongoing story. The galaxy breathes, and so do we. And in that shared breath, we find our connection to the cosmos. Now that we've journeyed through the space between stars, now that we've traced the cycle of matter from stellar cores to interstellar clouds to planets to life, now that we've understood the galaxy's breath, what does it all mean? This is where science gives way to reflection, where data transforms into wisdom, where understanding becomes meaning. The interstellar medium, this vast, thin ocean of gas and dust, tells us something profound about existence, about time, about our place in the universe. And sitting with that, really pondering it, can change how we see everything. First, there's the meaning of connection. The interstellar medium shows us that nothing in the universe is truly separate. Every star is connected to every other star through the gas that fills the space between them. Every planet is made from material that once drifted through that space. Every living thing is built from atoms that have journeyed through countless environments over billions of years. We are all connected, not just metaphorically, but physically, chemically, historically. This connection extends across time as well as space. The atoms in your body connect you to stars that died before the sun was born. They connect you to the first generation of stars that formed after the Big Bang. They connect you to the future, to the stars that will form billions of years from now. You are a link in a chain that stretches from the beginning of the universe to its end. What does that mean for how we live? Perhaps it means we should see ourselves less as individuals and more as participants in a larger process. Perhaps it means the boundaries we draw between self and other, between human and nature, between Earth and cosmos, are less real than we think. Perhaps it means that caring for the world around us is not altruism but self-interest, because we are literally made of the same stuff as everything else. Second, there's the meaning of impermanence. The interstellar medium shows us that nothing lasts forever. Stars form, shine, and die. Planets coalesce and eventually disperse. Even atoms, stable as they seem, will one day decay as the universe expands and cools toward heat death. Everything is temporary, including us. This could be seen as depressing. If nothing lasts, what's the point? Why does anything matter? But there's another way to see it. Impermanence means that every moment is precious, precisely because it won't last. Your existence, brief as it is on cosmic scales, is rare and valuable. The specific arrangement of atoms that is you has never existed before and will never exist again. You are unique, not despite your impermanence, but because of it. Impermanence also means change is inevitable. The interstellar medium is constantly evolving, cycling matter through different forms. So too are you. You're not the same person you were 10 years ago, or even 10 minutes ago. Your atoms are constantly being exchanged with the environment, your cells regenerating, your thoughts shifting. Change is not something that happens to you, it's what you are. Third, there's the meaning of scale. The interstellar medium operates on timescales and distance scales that dwarf human experience. A single breath of the galaxy takes millions of years. The nearest interstellar cloud is light years away. These scales are almost incomprehensible, and yet understanding them gives perspective. Our problems, our anxieties, our conflicts, they matter to us, of course. But in the context of cosmic time and space, they're fleeting. 100 years from now, most of what we worry about today will be forgotten. 1,000 years from now, our entire civilization might be a footnote in history. 1,000,000 years from now, even our species might be gone, evolved into something else or extinct. This isn't nihilism. It's perspective. And with that perspective comes a kind of freedom. If everything is temporary, if nothing matters on cosmic scales, then paradoxically, everything matters right now. You're free to choose what to value, how to spend your time, what meaning to create. The universe doesn't impose meaning on you, you create it. Fourth, there's the meaning of complexity. The interstellar medium shows us how complexity arises from simplicity. Start with hydrogen and helium, the simplest elements. Add gravity and time. Stars form, creating heavier elements. Those elements mix in the interstellar medium, creating molecules. Planets form, creating even more complex chemistry. Life emerges, creating biology, consciousness, civilization. Each step builds on the previous one, adding layers of complexity. This suggests that complexity is not an accident. It's a natural consequence of the universe's laws. Given enough time, simple systems become complex, and that complexity is fragile, dependent on specific conditions, but also robust, finding ways to persist and adapt. You are an example of that complexity, a system so intricate that you can reflect on your own existence, ponder the meaning of the interstellar medium, and create art, science, and culture. Fifth, there's the meaning of purpose. Does the interstellar medium have a purpose? Not in the sense of an intentional design. The universe doesn't have goals, but there is a directionality to the process. Matter cycles from dispersed to concentrated and back. Elements become more complex over time. The universe evolves from simple to complex, from uniform to diverse, and in that evolution, purpose emerges. Not an imposed purpose, but an intrinsic one. The purpose of a star is to fuse hydrogen, not because someone designed it that way, but because that's what stars do. The purpose of the interstellar medium is to connect stars, to transport matter, to enable the cycle. And perhaps the purpose of consciousness, the purpose of you, is to be aware, to understand, to reflect on the process of which you are a part. This isn't a grand cosmic plan. It's simpler than that. It's the idea that purpose arises naturally from the structure of the universe, from the way things are connected and the way processes unfold. You don't need an external source to give your life meaning. The meaning is inherent in the fact that you're part of the cosmic cycle, that you're a way for the universe to know itself. Finally, there's the meaning of awe. The interstellar medium inspires a sense of wonder at the vastness, the beauty, the intricacy of the cosmos. It's easy to become numb to it, to take it for granted, to forget that we're living on a planet orbiting a star in a galaxy filled with hundreds of billions of other stars, all connected by this invisible ocean of gas and dust. But when you really think about it, when you let yourself feel it, the awe is overwhelming. And that awe is important. It reminds us that there's more to life than our daily concerns, that we're part of something larger, something ancient and ongoing. It inspires curiosity, the desire to learn more, to understand deeper. It fosters humility, the recognition that we're small and the universe is vast. And it creates meaning, the sense that being alive, being conscious, being able to contemplate the interstellar medium is itself a kind of miracle. So what does it all mean? Perhaps the interstellar medium means that we're connected to everything, that we're temporary but precious, that we're part of a process larger than ourselves, and that being aware of this is itself meaningful. Perhaps it means that the space between stars is not empty, and neither are we. We're full of history, full of potential, full of the same matter that makes galaxies and stars and planets. Or perhaps it means simply this. You are here, now, made of stardust, briefly aware, part of the cosmos looking back at itself. And that, in the end, is enough. And so we return gently to where we began, to the quiet side of the cosmos, to the stillness that fills most of the galaxy, to the space between stars. You've travelled with me through the invisible ocean, through the thin sea of atoms that connects every solar system in the Milky Way. You've learned that this space is not empty, but full of hydrogen gas, of dust grains, of molecules and magnetic fields and cosmic rays, full of history, of the ashes of ancient stars, of the seeds of new ones, full of potential, of the raw material for planets and life. You've seen the cycle, the great breath of the galaxy, inhaling gas into stars and exhaling it back into the interstellar medium. You've traced the journey of atoms from stellar cores through supernova explosions, into molecular clouds, into solar systems, into living things. You've realized that you are made of this journey, that your atoms have traveled billions of years and billions of light years to be part of you. And now, as this journey ends, or rather pauses, because the journey of your atoms continues long after this moment, I hope you carry with you a sense of connection, a sense that you are not separate from the universe, but part of it. That the space between stars is not out there, but here, in you. The legacy of the interstellar medium is profound. It's the mechanism that enables the galaxy to evolve, that creates diversity, that makes complexity possible. Without it, there would be no second-generation stars, no heavy elements, no rocky planets, no life. The interstellar medium is the foundation upon which everything else is built. But the legacy is also personal. The interstellar medium gave you your atoms. It shaped the chemistry that makes your body possible. It created the conditions over billions of years that led to your existence. You are a product of the space between stars, a temporary arrangement of cosmic dust, briefly aware and able to reflect on its own origins. and that legacy will continue. Long after you're gone, long after the Earth is consumed by the aging sun, long after the sun itself has shed its outer layers and faded to a white dwarf, the interstellar medium will remain. Your atoms will return to it, dispersing slowly back into the galactic sea. They'll drift through space once more, carried by invisible currents, bathed in starlight, waiting. Eventually, some of those atoms will be swept up into a new molecular cloud. They'll collapse with the rest of the cloud, forming a new star, perhaps new planets. The cycle will continue. Your atoms will become part of something new, something you can't predict or imagine. They'll take forms you've never seen, participate in processes you've never experienced. The journey continues endlessly through the ages of the galaxy. This is both humbling and comforting. Humbling because it reminds us that we're not permanent, that our individual existence is brief, that the universe will continue long after we're gone. But comforting because it shows that we're part of something larger, something that predates us and will outlast us. We're not alone. We're connected to everything that has ever been and everything that will ever be. The space between stars holds this legacy. It's the repository of galactic history, the medium of the cosmic cycle, the connection between all things. And understanding it, truly understanding it, changes how we see ourselves and our place in the cosmos. As you lie there now, in the quiet of your room, in the darkness of the night, imagine yourself drifting slowly through that space, not physically, but in your mind, in your imagination. You're floating between stars, surrounded by the thin, cold gas of the interstellar medium. Around you, atoms drift past, each with its own history, its own journey. Some were created in the Big Bang, others in the cores of stars, others in supernova explosions. They're all travelling, all waiting to be part of something new. And you're travelling too, even now, even lying still. You're moving. The Earth is spinning. The Earth is orbiting the Sun. The Sun is moving through the galaxy. The galaxy itself is moving through space. You're never still. You're always in motion, always part of the cosmic dance. The stars above you, if you can see them, are not distant objects. They're relatives, siblings in the galactic family. They're made of the same material as you, governed by the same physical laws, part of the same cycle. When you look up at the night sky, you're looking at your cosmic ancestry. You're seeing the furnaces where your atoms were forged, the environments through which they travelled, the connections that bind everything together. And the darkness between those stars, the seemingly empty space, is not empty at all. It's filled with the interstellar medium, the quiet ocean that connects everything. It's the canvas on which the story of the galaxy is written. It's the medium through which light travels, through which matter flows, through which the cycle continues. This is where we leave the journey, or rather, where this particular telling of it ends. The journey itself continues. The interstellar medium continues to exist, continues to shape the galaxy, continues to connect stars and planets and living things. And you continue, for now, part of that system, made of its material, shaped by its history. Before you sleep, before you drift away into your own darkness, take a moment to feel the connection. Feel the atoms in your body, billions of them, each with a story. Feel your breath. The oxygen you're inhaling, created in a star that died billions of years ago. Feel your heartbeat, powered by energy ultimately derived from the Sun, a second-generation star made from enriched interstellar gas. You are the universe, looking at itself. You are Stardust, aware. You are the interstellar medium, briefly concentrated into a form that can think and feel and wonder. And that, in the end, is the greatest legacy of all. Not just that the space between stars exists, but that it gave rise to you, to consciousness, to the ability to understand and appreciate the journey. The quiet returns now, the stillness of the interstellar medium, the peace of the cosmic night. You're part of that stillness, connected to it, made from it, and as you drift towards sleep, as your thoughts slow and your breathing deepens, imagine yourself floating gently through the space between stars, at home in the quiet, at peace in the darkness, part of the endless, ancient cycle that has been continuing since the beginning of time and will continue until the end. The legacy lives on, the cycle continues, and you, for this brief moment, are part of it. Welcome home, Stardust. Welcome home,